HDMI cable plug-in. Oh, of course.
Hey guys, everyone, thank you for coming. If you didn't already, there's beer and pizza. Be sure you get some of that. My name is Chris Gamble. I work for Supply Frame. Thank you. I also work on a site called Parts.io, which just relaunched as a brand new open search engine for parts. So when you're looking for, thank you. When you're looking for parts for your next design, please check it out. Parts.io is a great place to discover new stuff. This is sponsored by Supply Frame. If you don't know, you might have heard of some of the properties before. Mike from Hackaday is here. Hackaday is one of the properties. Tandy, Fine Chips, Parts.io, Code Effects you might not have heard of. You might hear more about it soon. Another unnamed company is not publicly, but it's sort of bought already. So anyways, we're all about electronics. We're all about data and helping you find parts for your design and actually getting stuff made. That's a big part of what we're doing. So we love this event. It's our eighth one? Eighth one, right there, big 8. So it's our 8th one. I got some great speakers lined up, and we're really excited about it. Before we do that, we're going to have people. So if you have something you'd like to announce, something you'd like to talk about, if you have work for others, if you're looking for work yourself, if you have a startup you'd like to mention or a project you're working on, 2 minutes. The clock will be ticking, and we will. Yeah. So why don't you come on up, and we'll have our first one.
Thank you. My name is Owen, and I do tech writing and editing, blogs, research proposals, articles, web pages, presentations. Looking at my card here. I've already talked to you, a couple of you already. But please, by all means, if you have that need, talk to me afterwards, after presentations. Thank you very much.
All right. Thank you.
Hi, my name is Bill Weiler. This is totally unrehearsed. I didn't know we do this here.
We didn't either.
Yeah, good. We're all in the same spot. So I'm a former engineer. I recently came up with a startup doing Bluetooth Low Energy. I also do hardware. My meetup is South Bay Embedded Designers, and we set the Tech Shop San Jose in about a week. And we'll be going for about 6 years. And you can also catch me on Instructables, where I did the refrigerator shirt. Sounds just like it is.
Hello, my name is Kelly. I'm a software and hardware engineering. I'm several friends who are working on AR and VR headset. This is like a crappy for hacking. So here is the have Android phone, which which running a game demo. So which has a stereoscopic field, have like a bright eyes. So if you stick it onto your phone, we have a better 3D print frame. If you see it, you could see like a 3D gaming that if you add in some more things, you can interact with it. So we are keep updating the lines and also making a breakout board for it. So for anyone interested, I could show a demo later.
Awesome.
Hi, my name is Andy. I've got a project that I've just been roped into that is grown out of some really interesting work a friend of mine's been doing down in Brazil, working with people in, I don't know if you've heard of favela. It's basically these hillside, shanty towns. Kite fighting is a really popular pastime down there, and she put some electronics onto the kites that people are using, and it was a big hit. So we're trying to turn this into a product. And I'm looking for people that can help think about ways of doing incredibly cheap, incredibly light electronics, basically an IMU, maybe powered by a solar panel, creative ways of docking and getting the data off in order to build something that will be fun for people all over the world to play with. So please talk to me if you have some expertise that's relevant. Thank you.
Anyone else? Yeah. All right, come on. Carl just had a wonderful guest on the show.
Yeah. So my name's Carl. I do a small podcast called the Spark Gap. Anyway, I just interviewed this really terrible guest. The interview will be out Wednesday. It is part 1. It was this guy, Chris, mostly talking about parts I own, a little bit about op amps and stuff like that. So might be a good one to check out.
All right. Love op amps. All right, anyone else? Yes? No? Yes? All right, cool. So our first speaker is Kai. He's going to be talking about speakers for a project for something. Sorry, not speak. More audio systems. Yes, I'll tell you all about it. For some kind of tiny festival that happened in a desert somewhere. I don't know what it was, but he will tell you all about it. So, please welcome Kai.
Okay, so let me preface this. I'll preface this by saying that this is a project I did entirely arbitrarily. Right? So much of my work is for clients and it's wrapped up in NDAs and it's their technology and my inventions, and I can't really talk about it that much. This is something that's totally outside of that. This is something I did because I felt like it. I did it because I thought we needed it. I did it because I thought it would be fun. Connectors on the side. Okay, so I'm calling this adventurous and ambient audio. That sort of alliteration is something that Chris Gamble is very fond of. And this was something I made for this little festival in the desert called Burning Man. Let's start with last year. So I'm part of this camp that just randomly throws things together at the last minute, and everything seems to work out pretty well. And last year's setup for audio and mixing, I don't know how well you can see this, but this is my friend Lawrence, and he's sort of chanting into a microphone that's hooked up to some who knows what that somebody found somewhere that hooked up to some sort of power supply. And it was really totally random and sort of a mess, but a lot of fun at the same time. So we said, in the future, let's take audio seriously. Let's find a way to let's try to do something serious as far as audio goes, right? We like our music. There's loads of music there. We want to have music, and we want to do it in a way that is environmentally responsible, meaning not running a generator all the time. There's enough noise as it is. There's enough pollution as it is. This is supposed to be an event where you try and discover new things rather than just do things the dirty old way. So we have solar panels. These are two of my other friends here setting up a solar panel on top of one of our domes. Yes, of course we have domes. If you know about the event, there are way too many domes out there. But they're good for solar panels because they get the panels up and can get the sun. So we had this goal, which was to make clean, responsible, solar-powered audio. And I thought, okay, we can give that a go. So the objectives are low power. This is like low audio output power and low power consumption, about 5 watts or so per unit. The next goal was to run from a bank of 12-volt deep cycle batteries, which is what we have in our camp. We run our lights off them. We run some other things off them, like we charge phones from those things. And they're all charged up from the solar panels. They asked me to build 16 to 20 units, whatever these units are. They said, wouldn't it be interesting, instead of having a single speaker or a single pair of loud speakers that consume a lot of energy, to get the sound out across the camp or whatever it is, you have to make that central source of audio very loud. I mean, this is the same sort of problem as a radio tower has to broadcast with many, many kilowatts of power to get a radio signal far away, whereas a cellular system has lots of little towers that broadcast with less power and covers a larger area, so it doesn't have to be quite so loud in one place. Radio versus audio, same thing, more or less. And I have this ridiculous budget, which is like $250 to develop this thing. So what did I come up with? Well, I came up with this. You can see one right here. So it looks, unsurprisingly, like a little speaker. The goal was to distribute a bunch of these around our camp. And of course, because they're an asset of our group of friends, we can use them for barbecues and camps and whatever else it is that we do. We throw multiple parties and fundraisers around the year, all centered on this sort of annual activity that we do. So I had this problem initially, which is like, okay, I want to build a speaker. How do I wire it? Is the speaker just a couple of codes, like a woofer and a tweeter in a box with some connectors in the back and then a bunch of wires in them, run to a central amplifier? Sure, you could do that. But the con here is that it does require one central amplifier, and it has to have many different cables all coming into it at the same time. Right? And that has to be a special kind of amplifier that has many different output channels, right? Because you can't, of course, parallel a number of different speakers altogether, because the net impedance on that would be like 1 ohm, so it's not designed for that. So it also requires a lot of wiring. You have this sort of star topology where you have one big amplifier in the middle, if you can even find that thing. It has many different lines all running out to different places, snaking around the camp, carrying the full power of the speaker and the full signal too, because they're one, right? When you do that. And that wiring has to go everywhere. Obviously, you then have power loss over those long runs. And if you're carrying the power required, oscillating back and forth to drive the speaker, then you'll have all the sort of signal integrity problems. Right? That goes without saying. You need thicker wires, which increases the cost of the system, thicker wires to deliver that signal and that power, because they're the same thing. And then there's a practical problem. Where do you get a 20-channel amplifier? And what if they ask me to build 50? Right? Like, where do you get that? Do I have to bring some sort of rack mount apparatus out there on wheels? And then bring it to all the other events that we do? I mean, what even is this? And honestly, I didn't even really bother to investigate this, because I just thought it was kind of ridiculous to push all the complexity into one multi-channel sort of amplifier. What am I running here, like a cinema? So furthermore, if I did find something there, would it run efficiently on 12 volts? I think it kind of strayed away from the goal of like, make some small, clean, power efficient. And I probably can't build it myself. Might have to get some sort of off-the-shelf equipment for it. So the other idea I had was, what if every unit had its own amplifier inside the speaker? That's possible, right? There's a positive here, right, a pro, which is that every unit takes only power and audio input. So you decouple, of course, you separate the power from the audio signal itself. You can maintain better signal integrity when you do that. And yes, I know it's just audio, and yes, I know that a lot of PA, especially at that event, is not particularly high quality, but I have some standards. So you can put these wires in parallel, which, as I said, decouples it. That's better. You can make it more distributed and more failure tolerant, because if you have one big speaker in the middle, one big amplifier in the middle, I mean, and that should fail, well, then you lose 20, or you lose 50, or whatever it is. It's just not scalable to concentrate that much complexity in one place. So this is more failure tolerant if you have multiple copies of the same thing. So another positive is that I can make it myself. I don't know if I can really lay out, in the minimal time and minimal budget that I have, I don't know if I could lay out and manufacture one really big board with like 50 output channels or whatever. Even the 20 that I needed, how can I even do that? Where would I start? So another benefit of having separate systems is that I can break it up. I can build it incrementally, right? Because it just scales unit by unit by unit. This is sort of like scalability of network services in the cloud. You can just spin up another one when you need it. And that makes it really fun. You can also split it up into 2 pieces or 5 pieces, right? You have multiple different things. We had 2 of those domes you saw in the corner of in our cap, and we could easily have like intense music in one and peaceful music in the other. Anything's possible. So then there's the other issue of like, you put the amplifier inside the speaker itself, then you have all these signal lines running all over the place, and then there's the question of like, what is the impedance of each one, the impedance of the amplifier? What does it look like when it's in parallel? And then there's the issue of noise, and that's really the one that annoyed me. I said, like, I'm going to spend all my time trying to make the signal good enough quality on this, rather than just having fun. And the whole goal was having fun with this project. So if you're not familiar with this, I'm certain most of you here are. There's this question of like, what is the infinite impedance? This is the most simplistic possible way I can illustrate this. But what happens if you have many of them? It's the equivalent of all those being in parallel, and then it's parallel impedance and so on. Anyway, so here's the third idea. What if I had a digital amplifier? And what is that? Well, it's digital circuitry inside the device with some sort of amplifier on board. Now, I don't know if this is a wacky idea, but part of the reason I wanted to give this talk is because I couldn't find anything like this. I could only find speakers that took like SPDIF inputs and other things. I couldn't find some sort of general purpose network speaker topology. It may exist, maybe inside Dolby or something. If you know about it, please talk to me afterwards. But I thought it'd be fun to build a digital speaker network. So we have all the benefits of the integrated amplifier we saw a moment ago. In addition to that, we can also have the benefit of a digital network is very noise tolerant, right? So if it was like Ethernet or something like that, that's like a well-defined, well-understood system that's really tolerant to noise. It's not affected, oh, that sounds better. It's not affected by the amplifier input impedance because it is digital. Of course, that's not a benefit. Now, here's where it gets really exciting. It can be bidirectional, right? If you have a digital design, a digital network of your own design, you can have information go both ways. You can have a motion sensor in here or something that tells the central system or tells other speakers when there's motion nearby. Like, who even knows? There's all kinds of different possibilities you can go with. So that's really exciting to me, that it could be a bidirectional network. You can send other data, of course. One of the downsides of this is that the transmitter is no longer trivial. It's no longer just some way of buffering an analog signal and sending out through the network to all the amplifiers. You don't have to like encode the audio and like put it into frames. You'll see what I did about that in a moment. I don't think it's that difficult, but it's non-trivial. The network itself may also need repeaters and termination. So this is true of high-speed designs, and many of you will be very used to this, but for a regular analog audio network, you may not have to do this. This is strictly a downside. Okay, so digital could be more complicated, right? And I had very limited time to do this. I was doing it just in the evenings, late at night, blasting these speakers, but nobody else was in the office. There's a tool for this, though. There's a tool to make digital networks easy, and it's the humble serial port. We use it all the time for all manner of different things, and it's a really cheap and easy way to get a network working without having to worry about like bit synchronization and warbles at the beginning of a packet and Manchester encoding and all that sort of stuff. So asynchronous serial is really flexible and durable, right? I picked it for this project because it was dumb and straightforward and simple, and everything has it. It's very easy to test, very easy to measure. You could do it with nothing more than a single data line and ground, of course, to transmit all the audio data you need. And that has terrible signal integrity, especially over the distances that I was working, so we won't do that. But there is another way. There's another way, and that is RS-485. Equally dumb and simple, but it's differential, right? It's differential. It's really easy. You see how difficult audio is?
I'm sorry. Right there, Chris, stop.
Okay, good. So RS-485 is a really dumb, simple, inexpensive, easy to get working in a limited time, cheap, all these benefits, way of sending a high-speed or low-speed, whatever, differential data stream to a bunch of different devices. You can have a multi-drop bus, which means one sender and many receivers. You can flip the rolls back and forth. It uses just 2 wires. It isn't encumbered by patents like CAN. Those of you who have worked on car networks will know what that's all about, or LIN bus or anything like that. It's just cheap and easy, and it's fun, right? That was the whole goal with this project, just to remind you. There's no dedicated clock on this, right? It's basically, you can use it however you like. I don't know if there's even an official specification saying this is how you have to use it, and this is how frames look. I think they just say, we create a differential output, and then the data sheet ends there. It's like, that's it. That's all that there is. There's just an A line, there's a B line. The inputs are defined as some amplification of the difference between them, and there's the truth table if you want to think about it digitally. So when it sends a 1, it transmits a low and a high, and then vice versa for a 0. And when it comes in, there are these 2 ambiguous points. If the common mode, if the differential mode voltage is below 200 millivolts on the particular receiver I was using, then it just doesn't know what to do. And that would be noise. That'd be useless noise anyway. So let's not worry about that. So here's a block diagram of this digital amplifier thing I made. So there's an RS-485 front end, you might call it. I used a chip from TI called the SN75176, which can go both ways. It can transmit or it can receive. I had a bunch of them lying around. It did the job. The microcontroller I used was another part I just had lying around. I'll explain that in a moment. It did have USB, which meant that loading firmware was really easy. I didn't want to spend a lot of time loading firmware on these devices with a JTAG connection or something. Definitely, I was designing for durability. I knew that if I was out there in the desert, everything breaks out there. If you haven't been to Burning Man before, it is the killer of all things. It will eat your bikes. It will destroy your electronics. It ruins your shoes and your feet. The dust out there is very alkali, and it's probably the most horrible substance. I think probably engineering for the surface of Mars might be a little bit easier than this, because you get all your products dusty and it destroys ball bearings and it corrodes your electronics and everything. When you bring them back to a higher moisture environment, because it's very dry out there, a high moisture environment like here, that alkali dust draws all the moisture out of the air and immediately rusts and corrodes everything, right? So I had to design stuff to survive, and I knew that if I was out there and something didn't work, a USB bootloader for firmware can be a lot nicer than a little JTAG connection, which could possibly go backwards and then things blow up. So that was nice. The DAC I used was another sort of part I had floating around, as with the amplifiers. I'll go over all that in a moment. As you see, there is an analog path here. The analog path is those passive filters, indicating those 4 blocks. And then the speakers at the bottom. They look kind of like rocket thrusters, but those are speakers. There's also an SMPS, a switch mode power supply, converting the 12-volt system voltage of our deep cycle batteries. It actually varies a lot more than that. It converts into the 5 volts that we need. Right? Very simple stuff. Dumb and simple was the goal here. I had limited time and very limited money to do this, and I didn't want to just put it off. I didn't want to fail. So here's the thing I keep getting at. Like, how do you start with a project like this? I'm sure many of you do this professionally here, right? And maybe some of you do it as a hobby, and probably another set does both. How do you get started? I don't know, if you're like me, then you think of all these weird and wacky ideas all the time. It's like, oh, I really want to make this, and I want to make that, and maybe you start and you get halfway or something, and then you get stuck on, oh, it's really difficult to figure out how to write assembly code for this wacky chip that's really interesting, and then it just dies. I was committed with this project to get it done on time, in my spare time, under budget, and not lose my mind. And so you have to go dumb, you have to go very simple with it. You have to go with what you have and what you know, right? And for this reason, this is probably going to be the least interesting, technically, talk of all the ones here. But I did get it done, right? So this is also the key to staying under budget, is use what you have. So I had a lot of parts sitting around from previous builds, like junk box sort of things. I desoldered a number of parts to make this possible. And here are the leftover parts that I had. So I had this ARM Cortex-M3. It was one of the first ARM Cortex-M3 microcontrollers released years and years ago, like 5 years ago at this point, maybe more. And I just had a bunch of them sitting around. So great way to cut costs, just use some part, whatever you got. Same goes for this one. It's just a DAC. It's a stereo DAC. I think NXP designed it for TVs in the 90s or something, and it's just had a bunch of them sitting around. It's a pretty good job. It doesn't require any sort of clock source, any master high-speed clock. It has a PLL inside there, and you just send it. I don't want to sidebar on this, but you send it like the basic clock that tells it when to toggle left to right. If you have any familiarity with digital audio or I2S or something, this is the heart of all those signals. It takes that and it uses a PLL to multiply it up to the right sort of sample frequency, and it just works like magic. This is definitely like an Arduino class part because you really can't mess it up. Wonderful. And it's stereo, right? Stereo, and it's 24-bit, and you can throw, I think, 96 kilohertz sample rates at it, which I was definitely not using, but you can do that. So that's great. I also had this little audio amplifier. This is another wonderful chip, another SparkFun special. You can get these all over the place. It's a tiny chip. It's like 3 by 3 millimeters, a Class D amplifier, really easy to use, and it delivers spectacular bang for the buck. It's not powerful at all. It's like 1.65 watt, I think, total output. But it's very easy to use. You almost can't go wrong, and I think it requires something like 6 components around it, no bigger than 0603. So really easy. These are all dumb, simple, predictable parts. And finally, an SMPS chip that I really don't like, but I had them sitting around. It's really inefficient and just horrible. So I'm sorry if anybody here works for diodes. Or anyway, I don't like this chip. They make other good stuff, but I don't like this one. I had a bunch though. I have one of those ridiculous, 12-inch reels of inductors that work specifically with it and almost nothing else. So I had that sitting around in my closet and just said, okay, let's just use it. Need to get this thing done, right? I didn't have any nice Texas Instruments switch mode supplies or anything. So I just used what I had. So here's the block diagram of the overall system, right? We have a front-end, analog front-end, a microcontroller to digitize, an RS-485 interface to put it on the bus, and a whole slew, many different copies of the same receiver, which is RS-485 receiver, microcontroller to demodulate, if you will, and then a DAC to generate the analog audio stream that gets amplified, right? Pretty predictable. Nothing here should surprise anyone. And that's what it looks like. So this is where it gets really fun, right? Because I made a little circuit board, and I found this part on Parts Express, which is if you don't know it, it's a vendor of all kinds of audio stuff. And they sell on Amazon, they sell directly. They have, if you want to build your own speakers, this is the place to start out, I think. And they ship everything from their gigantic warehouse in Ohio. I don't know how you guys have so much space in Ohio, but there's this huge warehouse and they ship everything out from there, and they got everything, right? So this is a little like connector type gadget. You can see the back of it here, and the other photo is the other end. So it's like spring terminals. And typically this is installed in the back of the speaker, right? And normally you just wire up the speaker drivers themselves to this, or maybe you have some sort of a passive high pass, low pass, crossover, whatever filter that's on it with gigantic inductors on it, gigantic capacitors, because the low frequencies of audio that we hear, you need really big parts, really high values of parts, right? I didn't even mention this in the presentation, but this is another thing that I optimized out, because I didn't want to be putting gigantic inductors in this thing to get a high pass and low pass. You'll see what I did in a moment. But this is a little circuit board I designed and fabricated with Oshpark that bolts directly onto those little spade terminals of this thing, so that I could make one integrated PCB that fits in the back of the speaker. So the whole thing, and I'll pass this around later so you can see it, but the whole thing just looks like an ordinary speaker from the outside. But really, it takes, as you can see in this photo, a 12-volt supply, ground, and then a differential negative and positive input from the network, and that's it. That's the whole thing. It takes care of all of its own performance and whatever. If the voltage supply droops, it doesn't care. It can go down to 6 volts and still work. So that's, that's cheap, durable, fun. Now let's talk about data. My background is in software, right? You can probably guess from this that I don't have a EE education or that much EE experience in the big scheme of things. I think it's really fun, but my background is software, and that's what I take really seriously. So let's talk about how this works. The software is really, really simple. But first, let's define what audio for our purposes is, right? It's AC signals. It's a superposition of AC signals ranging from 20 hertz to 20 kilohertz. It's a crude definition for the purposes of this project. That's roughly the range that humans can hear, just as you're curious. So an analog data stream, right, a signal, we can quantize, we can sample it with an ADC, an analog to digital converter. Now, I could use a really fancy ADC here from like, analog devices or Berggren or Wolfson or something like that, right? But again, cheap, simple, what do you have, what can you make work? How can I avoid the pitfalls that will cause a project to die before I went there in August? So I have this really crude, like what's the simplest possible front end I can make to turn an audio signal into something that the ADC in my little ARM Cortex M3 can interpret, right? Let's start there. Is the noise performance going to be good? No, of course not, right? Is, is the frequency range going to be the best that it can possibly be? No, it doesn't matter, right? I'm just trying to make something that's simple. So I use this this op-amp here, right? And then its input is basically decoupled by the capacitor. Many of you probably know this much better than I, so I'll leave you to it. And I simulated this in my most favorite terrible simulator, which is the Falstad one. It's now available on the web, but I'm using the Java version here because years ago I rewrote whole parts of it to simulate stuff better and to look at the power dissipation of things. So, yes, it's not sophisticated at all, but it's mine now. Right? I've made it mine. Okay, so typical line-in audio, for those of you who don't know, is considered 2 volts peak-to-peak, like a voltage signal, with an expected impedance of 10 k-ohm on the receiver, apparently. There's some standard or something, I found that somewhere. So that's all that this front end does, is it sort of adapts that signal to match, the 0 to 3.3 volt ratiometric range of the ADC. Yes, this is not a differential ADC in this microcontroller. These are pretty rare. Okay, so audio streams are continuous, so I break them into packets. We're talking data now, right? So I sample the ADC a whole bunch at some sample rate, and then I have to transmit that thing. Now I can sample it continuously and then just send those samples, but that's really hard to synchronize with. You can't fit other types of data into the data stream, so I packetize it. This is an incredibly trivial operation. It's the foundation of almost every protocol I can think of right now, is packetization. So the transmitter samples, compresses the audio, and then sends the packets. So on the receiving end, the receiver decompresses it, does DSP, and then feeds the DAC with that result. We'll look at each one of those stages right now. So audio compression. I picked the G.711 standard, not just because it has a nice ring to its name, but also because I knew it from a previous project. It can be implemented very trivially. Is it the best performance? No, but it has incredibly trivial computational cost. Right? There's no frequency, there's like no discrete cosine transform, no Fourier transform. None of the fancy stuff you get inside Speaks or whatever else. You can implement it in like 7 lines of code. So I'll show you those. So this is basically what it is. It's what's called a compounding compressor. It takes a 16-bit, technically 14-bit input, and it turns it into an 8-bit or 1 byte output. Very simple. And it operates in a stateless way, which is that every input sample turns into 1 output sample. That's it. It doesn't look at like 1 block and then frequency decompose them and whatever, the sort of things that MP3 does. It doesn't do any of those transforms. So very simple, very fast, doesn't require anything fancy to do it, all software. So the way that you implement compression is to basically look at it like a tree, right? It's like a binary search tree sort of search. The input sample will fall within some range, and the range, each range changes size, which is why you have to use a tree for this, rather than just like shifting or chopping up some bits. So you do this search to find where it is. Imagine that we go from the root node, and the input sample, which is in the range negative 32,767 to positive negative 32,768 to positive 32,767. I knew somebody would catch me out on that if I made a mistake. So that input sample comes in, right? That's considered like a 16-bit signed input sample. And you follow on this tree. If it's lower than, you take the left in every case. And if it's greater than or equal, you take the right. So if we follow it here to like negative 1852, and suppose our sample passes through that one on the right side to negative 364, and then passes on the right side again, that's the encoding that it will turn out with according to the table. So the prefix, the nibble prefix is 0100, and then ABCD is the actual value in that range. So what G711 does is it compresses this wide range into a smaller set, providing more bits of resolution. That's the ABCD. We'll go back a slide so you can see this. More resolution really in the smaller ranges where audio tends to be than in the larger ranges where the error isn't as noticeable. That's all it does. So here's the implementation of the compressor. Now this one is in 7 lines, but it's still pretty simple. It's very predictable. It's just a number of nested ifs, right? Big deal. What you could do is you could do a linear sweep saying, does it fall in this bucket, this one, this one, this one, this one sequentially, but of course that's like big O of the number of buckets, which in this case would be 16, with like a statistical likelihood it will fall into one of 8 each time. So it's essentially like big O 8, I might call it that way. This is slightly better because I'll use this tree to say, is it greater than or less than 0, and then go from there. So it should do it in 3. So if, well, 4. Okay, so it generates this audio packet that's now compressed, right, on the transmitter. It puts this header out there, and I'll explain what the header is in a minute. But it starts with the same 2 synchronization bytes always, and those are 7F, E0. There's no reason why those are special, but they're just special. They do have to be there. The receiver also doesn't look for like gaps in the signal. It just looks for those 2 bytes and then a header. Could it make a false positive on one particular packet? Absolutely it could. But the amount of time that a packet represents is very short, and all you'll hear is the same sort of noise as if you like plugged in the power or something, tiny little pop. So I didn't really go to great lengths to make sure that this was bulletproof. There's also a command phase, I'll get to that in a second, and then there's the block of audio bytes. In this case, it's 320 samples, and that's it. That's what it looks like on an oscilloscope. On RS-485, it's differential, right? So those signals swing around, and let's enhance. And then we'll separate these. So that's what it looks like, right? I mean, and if you've looked at USB before, that's more or less what it looks like too. Differential signals are differential signals, right? The range that they operate in is often different, but that's it. That's it. And the really nice thing is this took so little time to get working because it's simple and easy. Right? Okay, on the other side, we've got to synchronize and decode this. So we have these different steps, which is synchronize the beginning of a packet, and that's that 7FEO that we saw. We have to decode the command phase. That was what was highlighted in the previous slide. We have to decompress the audio. We'll get to that in a second. And then once the audio section of the packet is complete, we desynchronize. So the state machine enters the desynchronized state so we can synchronize again. And this is basically the state machine that I've got here, right? It's these different loops. If there are errors, one of these is an error handler. If the command phase contains an error, it just desynchronizes, right? So this allows it to automatically synchronize and ignore bad data. Yes, we could totally reinforce this with multiple different checksums. And in my professional work, I'm doing that all the time. But here, it doesn't matter. It's audio data, right? If it's a little bit noisy, whatever. Our ears will filter it out. So decompression, here's the same table as before. You can see essentially returning this middle column, right? The middle column is the encoded samples into the output value. And the output value is, as you can see, basically like the input value, but with a whole bunch of zeros instead of x's. And there's one there, and that has to do with routing and some other things. There's the decoder. Okay, it's not 7 lines, but it's very simple. And I found that the easiest way for ARM Cortex-M was to use functions in C and function pointers, an array of function pointers. It turns out, if you look at the disassembly, this is the nicest, best way to do it. Super small, super compact code, really, really fast performance. And that's it. It basically just says, what's the prefix? It's the first 4 bits. And the way you call this, I neglected to put on the way you call it here, but basically you just say, what are the first 4 bits? Take an index into that array we see in the bottom, and then call that function, and it takes care of the bottom bits. And it returns a sample to you. That's it. So I also do some DSP. And this is probably the worst DSP diagram you'll see, but I think it's correct for an infinite impulse filter. So on the top, we have this box, it's S1, S0. The arrow between them indicates that at the end of each cycle, or really the beginning of each cycle, we copy one to the other, right? So this is like a sliding window. And the other lines mean mix these different quantities. So each one of these is an audio sample. We have S, which is the source. We have the L track, which is the low pass, and the H is the high pass. And you can study this afterwards. I'll just basically say that the low pass samples the input sample and itself, and then the high pass samples 2 stages of the input, as well as delayed by 1 sample of itself. I'm not going to go into a bunch of DSP theory here. I will say, though, if you don't know it, it's sort of magic. It really does work magically. It's fascinating stuff. So the nice thing about this DSP is that it really just multiplies, shifts, and adds. So extremely simple for the CPU to do real time. You can do it in a very, very simple CPU. Now, why am I doing this? Because I need a low pass and a high pass signal out, which I put into the left and right channel going to the DAC. And those are fed to the woofer and the tweeter. I told you a moment ago that in many traditional speaker builds, they have a passive filter board. I don't know what the official name for this is, but it's a passive high pass, low pass filter. A crossover, okay. And that refers to the crossover frequency. Okay, as you sweep across it, the audio signal will go up to the woofer initially, and as the frequency rises, it will cross over to the tweeter. So often these things, particularly for high power speakers, are very large. They have huge coils, huge inductors, huge capacitors on there. And you'll see by doing this in software, yes, I make the trade-off in quality, but it takes no space and it has no cost. That's one of the reasons I love software so much. Okay, so I use this.
So you're dividing high and low like in a hard wall. It's either low or high.
No, not at all. If you see here, there's a parameter which is A and B.
Okay.
So I can pick those. In fact, I can transmit new values through the network onto the device and tune it, right, in the field. So I can pick those to overlap however I like, right? And the function can be arbitrarily complex. In fact, there are other things happening here. There's like an attenuation factor and some other things. We can do whatever, right? It's all DSP. So yes, it's not just a strict cutoff.
Okay.
But it is very simplistic. It's just one rolling, the function's just rolled out. Need in it. Okay, so we turn the digital samples into analog with the DAC. I use this woofer is left and tweeter is right sort of trick because every DAC that I found just had a left and right channel because they're all stereo, pretty much, right? You can get specialized DACs for like signal generators and so on that are single channel, but anything in the audio domain is stereo. So hey, you got it right there. Why not take advantage of it? The DAC, of course, supplies the analog audio to the amplifiers. It's going through that passive section. Left is the woofer, right is the tweeter. Okay, so the conclusion is it works, right? The whole thing worked, and that was really the whole goal, right? The whole goal wasn't to start a really cool project with ridiculous goals and ambitions and then like tell your friends about it and talk about it in front of a microphone and not finish it, right? I had a specific place to be. I had a specific number of these things to build, and I wanted to be able to use them. That was the whole goal. That's why I aimed a bit low. There's still some fun stuff in there, but I aimed low so that it worked, so that I got it done. And even though I've got some complaints, we'll see them in just a second, it's a good starting place. And the nice thing is, after having built these wooden boxes, which I did myself, I cut them all up and glued them and sanded them and so on. If I don't like something about the circuit, just replace it. It's just that little module in the back, right? You just cut it off and then replace it with something different. In fact, it reminds me, I've got some examples. I'll pass them around right now, and then I'll tell you what I don't quite like about it. So I'll send one this way, and the third one I'll just throw at somebody. That's okay. Okay, so let me tell you what I didn't like, because we can spend all our time complaining, right? But I'm complaining at the end of a completed project. So I'm talking version 2, right? I'm not talking like back to the drawing board, like all the other stuff I think of. So it's not powerful enough. Like, it just isn't. These 1.5 watt amplifiers I use inside the 1.65. They're really fun, they're really simple, easy to get working. They just don't have the guts they need. But that's an easy problem to solve. You can always get more powerful stuff. I got this other board here, also from Parts Express, with another Class D amplifier that's just bigger. I can swap this module in and try it out. In fact, I've already done this and basically blew the windows out. So you can do that quite easily. You can go to any sort of thing you like. This is a pretty specific complaint, and those of you holding the device will see what I'm talking about here. There is an exposed pad, like a pogo pin pad on the board for putting into programming mode. You hold it low, and there's another pad next to it. You'll see it's on the flat bottom/top, because it's actually installed upside down in the product. But it's on there, and it says something like bootloader or firmware or whatever. It was ridiculously difficult to press that button. It's not even a button, right? So I was like, when I designed it, I thought, oh, no problem. I'll just take something conductive and like stick it on there, I'll lick my thumb and touch it, which worked the first time. And I'll make it work. Or I'll put tweezers on it and touch the 2 points at the same time. Most difficult thing to do ever. I should have just put a button on there. I've got a whole reel of buttons. I could just put it on there. But at the time, I thought it would be okay. I don't know how many of you spend your days designing PCBs, but there's always this like, why didn't I just put a test point for this type thing? Well, this is another one of those. I should have known better. You can never have too many test points. And you'll see, if you look at the PCB, there actually are a few voltage test points. I think I've watched enough EEV blog videos to know thou shalt always check voltages. And I thought if I was in the field and something were to go wrong, the easiest thing would be take a multimeter and just check the voltage reads, right? And then after that, it's like, throw your hands up in the air, it's software. But that's the part that I know, so I was confident in that part. Okay, so it needs a programming button. Simple, gotta do it for the next one. It should have input protection. This is something that is so easy to do. You can just use a P-channel MOSFET and you put it in the input. There's this wonderful trick, you can go Google it, of how to protect against reverse polarity on the input. This thing has a ridiculously low impedance source for paralleled deep cycle marine batteries from boats, right? That could like kill somebody in a second. And if you put it on there backwards, there's no protection against it. I was in a real hurry and I didn't, I used space pretty efficiently on this and I didn't leave any for that. That's a pretty important thing to remember, right? Especially out there, it's dark and like somebody steps over the cables, they get yanked out, they go to put them back in again, boom. So easy to avoid, just remember it. And that's a reminder to me, mostly. The SMPS, I told you I didn't really like this one. It's not efficient at low current levels. I think I'll just spend a couple of pennies more or whatever for the next rev and put a nice TI switch mode supply in there. That does the same job, just does it much better. So here's my plan for the next version. You may be able to infer from my descriptions that analog is not my comfort zone. And if I could have an all digital, totally digital path, DAC and amplifier in one chip, and of course they make loads of these things. In fact, the TAS 5700 series is an excellent example of this that I've seen in consumer products and works really well. If I could do that, it's better. Again, costs. I didn't have any sitting in my closet, so I wasn't able to start with it. This is one of those sort of daydreaming, like, if I could design it again, I'll use this. Well, that's already underway. And again, I can say it because I finished. I want to have a big SPI flash on the next version of the product. Why is this? Probably because I didn't explain what ambient audio is all that well, right? Ambient audio is a distributed speaker network, but it could also be something else. It could also be these speakers play sound effects that are triggered by like motion or buttons, whatever else, and they're like chirping or making the sound of water running or whatever. You can use them for artistic installations, you can use them for, who knows? There are endless possibilities when you have a software-defined speaker platform. They can be playing store samples, whatever. Just thought it'd be fun, right? You send a command over the network that says, play this sound effect, and then just plays it. Halloween, anyone? So lots of fun stuff. A volume knob. There's no volume knob on the system, right? You basically have to attenuate the analog audio going to the transmitter, and it just transmits that as is, so it like loses a ton of resolution when you do that. There is actually per speaker attenuation support. And if you send a special command over the network, you say speaker 17, set your attenuation to this, just like you can do for the crossover filter parameters. But there's no knob for it. Like I just ran out of time and I wasn't able to make a knob. So I said, on your phone or your laptop that's connected, just turn the volume down. And it worked, but not great. I'd like to have a volume knob per speaker. I'd like to have a rotary encoder for it so it stores it digitally and can be overridden from the transmitter. Right? So if somebody turns it down, you can turn it back up again. Right? Not the only use case. There'll be other legitimate use cases too. Okay, and then of course, just a better switch mode supply. That's what I really like to have on the thing. And I think that's a pretty good Rev 2, right? I don't want to be shooting for the moon here. I just want to make another speaker that I can complete on my spare time and have it work. One second. I may also change the back panel connector. You may have noticed if you've looked at this thing going around that it just has those spring terminals. Very easy to make things backwards. In the original design of the circuit, I was coming up with this devious way where it's like, okay, with all of these diodes and things, I can make it so that the user can attach any cable in any port and it will still work. And it does technically work in schematic and simulation at least, but I didn't build it because I'm like, don't try to overcomplicate. That was the whole goal with this product, was just make it. Now, questions? Yes?
Any plans to do simplex powering?
Of course. The question is, any plan to do simplex powering? Of course, right? That's the reason why I keep harping on this thing, which is like, keep it simple. Of course, I dreamt up crazy ways where I was modulating RF and sending it over the power network and that sort of thing. What specifically were you thinking? Like a 2-wire setup?
Yeah, 2-wire.
Yes. I mean, of course, I thought about wireless. I evaluated different chips with a high enough bit rate on air to be able to send this. It's not out of the question, but the takeaway that I'm really trying to give you all here is like, keep it simple and just do it. Just finish. Right? That's the really important thing, because we can dream about incredible things all day long, like fiber optics that connect them and who knows what, right? But you know, you just got to keep it realistic. There's another thing I would really like to do, just before I answer your question, which is we discovered when we were out there, we spent a lot of time with wrenches and power tools in our hands building things. We had all kinds of stuff we had to build this year and also take apart. And we started using walkie-talkies, like actually they're little ham radios for the first time. And it was really useful to summon people. And I thought, wouldn't it be terrific if one of these was wired to the network? So if you call somebody a particular frequency, then it stops the audio and it sends out this page, and then it resumes the audio afterwards. Really easy to do from software, right? Wonderful like usability there. And I thought like, well, it sounds like the sort of thing you do to summon somebody to clean up a broken pickle jar in a supermarket. I don't know if that's really what I want to do in my camp, but it's interesting. Anyway, your question?
Yeah, I was just wondering, how much wire did you actually have to lay out?
Oh, I didn't even talk about the wire. I use Cat5, right?
Like,
Cheap and plentiful,
Was it
easy.
50 feet, 100 feet, how many feet?
I don't know, but we've covered it all because you don't leave anything out there. That's what you don't do. So I bought, I think, 500 feet and did not use it all. I'm sorry, I don't have an odometer on there or something to measure it.
How many of them were there?
Okay, I built 16 and not all of them worked, but I will not share my yield numbers with you. They were not that good. But anyway, but I know I can make more, and if I have a rigorous test procedure, right, to make these things. I built them all by hand, like in the middle of the night. So I didn't really expect fantastic results coming out of those things. And this is maybe something else I want to consider for the next version, is like more self-test abilities. But everybody says that about every product ever, right? So you just have to do it. Yes.
As far as inputs into the speaker, the speaker could be used as a microphone.
Yes, that's possible. Now, as far as an input, I have one of these. And in fact, I'm surprised I didn't demo it. I think I'll try to demo it while I answer questions. Any other questions? Yes.
Can we do anything more efficient on the coders, like ADPCM?
ADPCM, yes. I mean, it's always a trick. Sorry, question repeated. Have I considered doing anything more efficient on the coding, like the ADPCM codec? Yes. Let me think. From memory, ADPCM is it's a vocoder, right? So it uses a voice. Simulate and then store the error type model.
Yeah.
Right. Yes. It's just a question of code complexity versus results that I get out of it. The question is, do I have to use a 200 megahertz ARM Cortex-M3 instead of a 72? No?
Probably about 90 megahertz.
Okay, then I'll investigate it. Thank you for the tip. Yes.
So on this, the big thing is the cost, right? So you're doing the crossover on the encoding end.
No, on the decoding end. Yes.
Yeah. But if you were to move to the encoding, you could send 2 channels, one like a subwoofer from the low, which doesn't have to be as high bit, but maybe in a single channel, and then pass it. So they would just decode into 2 channels and drive that class to the direct. And you could use a much cheaper on PC speaker.
You're absolutely right. So let me see if I can repeat the question. If I moved the DSP to the transmitter instead of the receiver, then I can make the receivers cheaper. Yes, that's true. Would you suggest taking out the microcontroller then? Everything.
No, it would be very cheap, basically, because you would have like the low frequency, maybe 4 or 5 bits,
Yes.
and then higher frequency, whatever bits you need.
Yes, but you've forgotten that I had these microcontrollers already, so the cost was 0.
Okay, I'm just talking about you want to make that mass market or you want to make.
I have no idea what the commercial applications are, but I'll think about those at some time. So let me just power this on. Let's see how loud it is. I don't know if I've ever really conducted this. No, I've conducted this test already. Okay, so first of all, is it working? It has no LEDs. I tested this right before I came here. Okay, I'll see if I can get it working afterwards. You'll know it when you hear it. Maybe when we're mingling around or something. I'm not sure somebody else is talking. Yes?
What were the most expensive parts?
Oh, so there actually was an official cost breakdown. And the official cost was something like $5 of wood per unit. The PCBs were something on the order of yes, $5 or $8 or so dollars a piece. Recycling, all the parts were recycled. I'll get it working there. So yes, the costs were actually super low, but I was really cheating by just using junk hardware. Oh, that's right, the speakers. I think the speakers were something like $3 for the woofer and $1 for the tweeter. I really didn't know what I was buying because I'd never built speakers before, so I've just cost optimized. And they sound fine. Well, you'll hear it when it works. Any other questions? Yes?
Did you get the PCB assembled fully?
No, I assembled it by hand, all of them, late at night. So that's why they may be a little bit more toasty, more burnt than they should be. I did it with a hot air gun and other things. It's hard to see late at night when there isn't that much light around you. No, I did not assemble it in the desert. I assembled it at home before that. I did take my soldering iron out there, but I did not take a hot air reflow tool. Any last questions? Okay, thank you very much. Well, that's 2 out of 3. And afterwards, I also have one that you can, it's pretty predictable what's inside it, and you can take a look at all the pieces if you're curious.
All right, thanks, Kai. And Kai's going to try and get it working. We'll try and demo it between Mike and Matt's talk. So, next up is Mike. He's going to be going over 1 Pixel Pac-Man. Mike is the editor, chief editor. What's your managing editor of Packaday.com? You may know it. It's an awesome site. And Mike built this because this is DEF CON. He built this because you should build things at home, right? And it's a great little demo he'll have here. And he's going to tell you all about the history of the AI and how it was built and stuff like that. So give it up for Mike.
Oh, hey, it's working. Everybody has to be really quiet. So it does work. But as you can tell, it's pretty gutless. So the goal for the next one is like 25 watts per channel. So that's it. That's using the data stream. We saw over this ridiculous cable which I use for doorbells. But whatever, right? We use Cat5 for the actual site. There you go. Hack.
You could talk about sliding and slow.
You just want to see if you can hold it in our hand.
Hello. All right. Thank you for coming. My name is Mike Szczys. I'm managing editor of Hddg.com, and it's a great honor to speak at the Hardware Developers Didactic Galactic. I'm really excited for the opportunity. And I made something called One Pixel Pac-Man because I have the luxury of not making my living by building hardware. So I can make anything I want for any reason I want at any price with any length of time. And I generally look for things that are going to challenge me a little bit. I had built some games before, like Snake and Bouncing Ball and that sort of thing. And I was like, I kind of want to build something that is run on an embedded system and programmed in C and is a little bit more complex. And I started to look around and I'm like, you know, retro games are fun. Somebody else has already figured out the problem of how do you make it interesting. And I kind of went from there. And this is like the finished version here. So here's a little bit of the gameplay right here. And, you know, having seen Kai's talk, I now realize that that sound was complete BS. I just did that for the YouTube video because I figure anyone that doesn't watch past 30 seconds isn't going to know. But I don't have audio yet, but there is I2S on this chip. So, you know, that'll be like one of the future improvements. So when I started looking at Pac-Man and I'm like, hey man, Pac-Man's really awesome and I want to build it myself, I was like, how can I possibly compete with the hardware that's already out there? I mean, you have this amazingly pixel dense phone in your pocket at all times and you can go to the App Store and download Pac-Man 256, which is pretty awesome if you haven't tried it yet, for free. And if you don't suck at the game, you can play it for free forever. If you do suck, then you have to buy credits. So I was like, look, I can't, no matter what I do, I can't build something that has a screen that's going to compete with this. And even buying screens is tough. So I'm like, what if I do less pixels instead of more pixels? And, you know, the proof case for that is Minecraft, right? So Minecraft is crappy graphics on your, you know, $3,000 MacBook, but it's still super fun to play. So I was like, you know, there's maybe a use there. So then I started thinking, okay, less pixels. About 8 or 10 years ago, I built this display here, which is only 8 by 16, and hand soldered everything, and it took forever and was kind of, I mean, it wasn't an awful experience. It was fun to have done it once, but I certainly wouldn't want to do it with any more or do it again. And that's only one color right there, which kind of is awful. So that was a consideration. For user input, I definitely wanted to have something that felt like coin-op. And, you know, you can go, you know, I was conceiving projects as like people build main cabinets, that's already been done, this sort of thing. So I was like, I could build, you know, something with an arcade stick, but, you know, maybe there's some other way around it. And I did actually consider using MAME with a low resolution display. And I was like, you know, you could get some kind of Linux board, then you're not programming in C. But if you did get a Linux board, then you'd have to try and figure out, do you just downscale what's coming out of it, or do you have to like hack into it? And I was like, that feels kind of like a dead end. So I kind of ditched that and found out about this product called Smart Matrix, which is developed by Louis Bedouin, and I think the company is called Pixelmatics. And once I saw this, I was like, oh man, that's totally it. So it uses this panel right here, which is a commodity panel for like billboards, Times Square, that sort of thing. One thing that's really nice about it is that everywhere you can, the display is black. So if you're gonna just use it straight out, it has kind of a nice view on the back of it. It's full color. And in this kit, he actually makes it to go inside of a shadow box picture frame. And it comes with the diffusion acrylic. And if you ever work with LEDs, one of the big things is like, what am I going to use for a diffusing material? And it's like, that's already solved. It comes as a kit. And so really it's just this adapter board. And this is the back of the commodity panel. You can see there's I think that's a 2x16. Yeah, 2x6, or it's a 2x8, so 16 pins. There's an input and an output so that these can be chained onto one another. And the adapter board just like plugs into that. It's got some stuff, like it's got an SD card here, and it comes with some extra stuff that I'll talk about in a second. But really, I just wanted a way to interface with this panel. And that is done through a TC microcontroller, which I hadn't used before. But I looked at it and I'm like, man, that is a beefy microcontroller on there. Like, it should be fine. And as you know, because I'm thinking like, okay, you're scanning the matrix. You need to, do some kind of game code, all that stuff. So it's running fast enough. It's got a ton of I/O pins. And then after I really started looking at it, and I was like, okay, well, what do I need to do to scan the matrix? I don't need to do anything to scan the matrix. This chip has kick-ass DMA on it. If you haven't used DMA before, it's direct memory access. And so there's a library that was written for this product that totally drives the display. You've just got like 2 frame buffers. So you write into 1 frame buffer, and then you run execute a function that just swaps them, and then you write into the next one while it goes. And since it's DMA, you're really not using any CPU cycles. It's very minimal. And so in working with it, I'm running this really fast chip. But as far as my program goes, I've just got tons of horsepower to burn, which is really nice. It does come with IR remote control. And this kit, what it was being used mostly for is like animated GIFs or like generative patterns, screensaver type of patterns or stuff like that. And they had done, I think, using this remote control, like a Tetris clone. Tetris is another one of those games I programmed before. But the response wasn't good. If you've ever used these remotes, like they don't always read the command very well, and it's just not real time. So in order to get my joystick credit, I was like, hey, remember those really crappy Atari joysticks? I bet you can still get those, and you can totally get a reproduction for like $12.99 shipped. And it just uses a DB9 connector, so you don't have to cut the connector off the thing or do any of that. DB9 connectors are really easy to source. It doesn't use any kind of protocol. It really is just a button. There's like a common, and then up, down, left, right, and the big red button on it. So it couldn't be simpler. That kind of bites me a little bit later, which I'll get to. And so going back for it, really simple soldering project. It took me like, I don't know, 20 minutes to solder together. Fast processor, DMA. It's got the library already available. The buttons are super easy. And then the real killer is both the TC and the Smart Matrix are already in the Hackaday store, and I'm like, hey, Julian, who was running the store at the time, I'd really like to sample one of those kits. Can you send it to me? And then he just kind of arrived at my house. So now, as far as picking the game, Pac-Man's a great game to choose as a programming challenge for many reasons. The biggest being people are fanatical about it. And so like this is a book that was written for the coin-op version when people are like, how can I be the killer at the arcade, that everyone's like, wow, look at this Pac-Man score, that'll tell you like all these strategies to play the perfect game of Pac-Man. And most of those go along with what's the performance of the ghost, how does the scoring work, all that sort of thing. But of course it goes way further than that. People actually got the ROM and disassembled it and looked at all the code that's in it. And so there's this great web resource called the Pac-Man Dossier. And really like download this website onto your phone, and the next time you're stuck somewhere, you will start reading this, and then you'll forget your next appointment and just continue reading it. It's unbelievable how simple the Ghost AI is, but how real it feels. And it will kind of break the magic of the game, because if you look into how the ghosts perform, you'll start to see it, but I still have fun playing it. So I think you don't really have to worry about it. So when I started reading that, things got even better, because I had assumed it was some type of sprite game, and so I assumed the tiles were going to be fine. I found out that it was going to be 28 by 36, but if you look at it, several of the tiles, you get 3 tiles at the top and 2 tiles at the bottom that are being used for like scoring stuff. So you get it down to, I don't think that's quite right, because I'm pretty sure I used 31 by 28 in the actual board. And in order to implement that, it's really nice that the board is always the same. So I actually just have a constant array. And I should say, Pac-Man was my second choice. My true love is Miss Pac-Man. But if you've played a lot of Miss Pac-Man, you know that the levels change. And I figured that was going to be more difficult. So maybe 1 Pixel Pac-Man Part 2 will be Miss Pac-Man. So the board is always the same in the original Pac-Man, which means I just had a static array of bits, 32 by 32 bits, and wherever there was a 1, that was where you draw a wall, and that's also used for calculating whether or not you're going to run into something, whether you can turn, that sort of thing. And then I had a second array just for the pellets. So Pac-Man goes, I hope you've all played Pac-Man before. Pac-Man goes around, eats the power pellets once you've eaten all, or eats the pellets once you've eaten all the pellets, then you completed the level and you go on. So just 2 simple arrays, didn't need to worry about colors at all, because you just assume 1 array is the board and you draw that in blue, and 1 array is the pellets and you draw those in off-white, and it's good. As far as Ghost AI goes, as I read more, that's actually pretty simple. The ghosts only really have 2 modes. They kind of have a couple other quasi modes, and those modes use simple targeting. So you can kind of write these single targeting algorithms. And the added depth was stuff that I figured I didn't actually have to add in if I didn't have time or didn't want to do it. So the first mode that the ghosts use is called scatter mode. So when you start the game, for the first 7 seconds, the ghosts aren't actually chasing you. The ghosts are targeting areas that are off of the board. And every time a ghost gets to an intersection, it runs a check on that target, and it decides can I turn left, can I turn right, can I go straight, and which of those is, once I take that next step, which is closest to my target. One of the real key parts of the ghost is they cannot turn around. So if they're going forward, they can't turn around and go backwards. The only time they can actually turn around is when they switch modes. So when you're playing Pac-Man, if you see the ghosts turn around, they've just switched modes. So after 7 seconds, they'll turn around and start chasing you. After 20 more seconds, they'll turn around and start going to their corners again. Because they can't turn around, when Pinky gets to this square, it's going to look and say, is this closest, or is that closest? And obviously this is it. So it's going to go up here, do the same thing, go into the corner, and turn down because it can't go back. So it's just going to keep going around in circles. Everyone's like that. And then also, one of those quasi modes of going back to the house is just a target in the center. Each ghost has its own different choice for chasing you. So interestingly, if all of them were going to just chase wherever Pac-Man is, you'd just have a string of 4 ghosts right behind you. And it feels like they're smarter than that, and it's because of these targeting rules. So Blinky, the red ghost, does actually chase after your square all the time. And Blinky has a special mode that I'll talk about in a sec that's really devious and great game design. This is really one of the best games that's ever been designed when you start looking into the rules of it. Pinky targets 4 squares in front of wherever Pac-Man is facing. And here's where the fanaticism of people dissecting this game is amazing. If Pac-Man's facing up, there's actually a buffer overflow that causes Pinky to also target 4 squares to the left. So, and I implemented that bug because why wouldn't you? But I just think it's really interesting that someone not only figured out that that's how the targeting is, but it's also a bug and not a feature. Inky is, I think, probably the most clever of all of them. So this is maybe not the best slide for it. You'll notice that 2 squares in front of Pac-Man and 2 squares to the left is where this box is. That 2 squares to the left is because of the same buffer overflow on the other one. But basically, Inky looks 2 squares in front of Pac-Man, and then it reflects the angle of where Blinky is compared to that target around and makes that its target. And so what happens is, instead of Blinky ending up being behind you, Blinky always tries to be on the opposite side of you from where Inky tries to be on the opposite side of you from where Blinky is. So you get these 2 ghosts there kind of on either side. The third one, Clyde, he's got some weird, like, he's never actually chasing you. He chases you until he gets within like 13 squares of you, and then he goes back to his corner. So he's always kind of like being shy. And I guess that's another interesting thing. So these names are Americanized names. This is actually a Japanese game. And if you look at the Pac-Man dossier, they tell you the Japanese names for the ghosts, and their behaviors go along with the names. So this one is, I don't know, like bashful playfulness or something. All right. So some of the quasi modes, fright mode, when you get a power pellet, then the ghosts turn blue, or in my case, they turn purple because the game board is blue. And then they run away from you, but they're not actually making any decisions other than every time they get to an intersection they have to choose, it's random. And I already talked about going back to the house is basically like scatter mode again. One of the other things that kind of changes things up, there are a lot of speed tables in this, which is just really easy to implement because they're just lookup tables. But so for instance, the first level, it's like 7 seconds of scatter, 20 seconds of chase, and then it kind of goes back and forth. But those timings change each time, as does the percent of top speed that you can go and the percent of top speed that the ghosts can go. There's also some added things like going through the tunnel. Pac-Man goes full speed, but the ghosts go 40% of their speed. If Pac-Man eats a pellet, he takes a 1/60th of a second speed hit, and I believe that's because the game was at 60 frames per second. So it's just like a one frame, or maybe it was 1 clock tick hit. So if you have a ghost chasing you and you continually eat pellets, they could potentially catch up to you, depending on what level you are on that sort of thing. The Cruise Elroy mode that I mentioned before is like this really kind of complex set of different parameters for Blinky, the red ghost. Once you get down to the last maybe like 20 or 40 pellets that you have to eat, he gets this huge speed boost, and in many cases is able to go faster than you. So the less pellets on the screen, the more dangerous it is to be around the red ghost. I can't really go into that because it is a ton of different rules. That's where the game gets really complex, but I also think that's where you get that like jolt of adrenaline and get excited because you think you're going to finish the level, and then he comes and gobbles you up. And then I guess the last, you can't mention Pac-Man without mentioning the death screen. So, man, I can't remember the name of the guy who came up with Pac-Man. I'm sorry to him. It's on the video, you can look at it, but he assumed that no one could go through every single level perfectly. And so if you go through every level, eat every pellet, every time you eat a power pellet, eat every ghost, and if you eat every piece of fruit that comes up, you can play a perfect game. And when you get to level 255 and flip it over, that's, it's just a 8-bit variable. And so the game kind of freaks out, and it just draws gibberish on the right-hand side of the screen, but there are still pellets over there that you can continue to eat. And so the big thing is, if you want to get the highest score ever possible on Pac-Man, you have to take all of your extra lives and burn them, getting the unseen pellets while the ghosts are still chasing you. And there are several video game documentaries that cover this really well, so just Google it and watch those. Kind of fun. Oh yeah, so the thing is, I did appropriate the hardware from the Hackaday store, and we were actually out of stock on Teensies at the time, and so I completely wrote all of this without any hardware on hand, and I had never used a Teensy or the display before, so I was kind of lucky. But I just made a little SDL2 hardware emulator on it, and I was like, I'm so smart, I'm going to make all these files in C and make them all portable, so all I have to do is switch out the display and controller, and I'm going to put this together, and it's all going to work and be super awesome. Except for I don't really write for the Arduino environment before, and I don't really use C++ ever. I only really use C. So I wrote everything in C, but nothing in C++, and then the library for the display is in C++, and you compile it. I wanted other people to be able to use it, so you compile it and upload it with the Arduino IDE, and I couldn't get any of my files to include. I'm like, where is the make file so I can add this C file as an include? And as a kludge, like I just added it into one big file, even though everything was separated out, and spent like 6 hours, wasted like 6 hours trying to figure out why I couldn't do what I could do. And if you've ever mixed the two before, it's because if you're using a C++ compiler, you can use C headers, but you have to wrap them in this magic language right here. So gotcha, ha ha ha, that was fun. So the actual soldering was really super easy, but I hadn't looked into the hardware very much, and so I was like, okay, the Teensy has a bunch of breakouts, maybe like 11 more pads, surface mount pads on the bottom of it. So I'm like, okay, I'll use those surface mount pads on the bottom of it. So I soldered into it and to the DB9 and hooked it up. It works great. Put it all together and realized like the screen doesn't use any of the pins, 34 I/O pins. And so there's a ton of pins broken out on the side of this Smart Matrix adapter board. So I could have just used like a simple connector. But I'm happy I did this because I can make 2-player games if I just add another one on there. So I figure Miss Pac-Man 2-player, I'll lift them out at the same time. We'll see. And the joystick worked really well. I took it to the Layer 1 conference with me. It worked really well for like the first 5 people, and then it broke. They have these buttons. Does anybody know what these are called? What are they called? Snap dome. So they have these snap dome switches, and there's like this relief so that I guess you don't kill the snap dome. There's this plastic relief, but it ended up just breaking off. But don't worry, if you have bamboo skewers, which are one of my favorite repair devices ever, and some hot glue, you can put it back together. So I did that, so that was happy. And I think it's a successful project because it's been cloned a few times. So right away, the Arduino Enigma machine, there's a guy who's pretty active on Hddg.io. He cloned it like the next day or something. So I was like, yeah, that's really awesome. But even better, somebody wrote me and was like, hey, I'm going to the Orlando Maker Faire. Can I make your Pac-Man? And I'm like, yeah. And so he went and showed it at Orlando Maker Faire and got a blue ribbon. So by proxy, I have achieved a blue ribbon at Maker Faire. So, you know, I didn't really know how the hardware worked or care about it because things went really well. So check out, you know, some of these resources. Here's the actual project itself, but the TC board, that chip, it's a Freescale chip and it's super awesome. And the TC itself is really fun to work with. Paul Stoffergren has done a ton of work on the DMA libraries for audio, which I hope to at some point add audio to this. But those DMA libraries are what Lewis used to write his DMA libraries. And I think DMA is becoming a lot more prevalent in a lot of chips and not very many people are writing about it. And so like I've looked at the data sheets and it's not very inspiring to figure out like, how should I use this? What should I do? So if you're ever interested in DMA, those Paul Stoffergren's libraries for TeamC are great and Lewis's are based on them as well. This is the Smart Matrix, which includes library info. So if you want to see, like for instance, I have a game over that scrolls on the across the board, and I didn't have to do any of that font. And you know, if you think about it, if you have a frame buffer, you're going to write your letter into it, but then you have to remember what was under it because you've overwritten it. You don't have to deal with any of that. It's all built into the library, so super easy stuff. And then, like I said, Pac-Man Dossier, which has the world's worst URL, but you can just Google it and see. So that is the one pixel background. Any questions? Oh, I should mention it is here. It's on this table right here. So we'll fire it up at the end and you can play it.
I think you're taking over.
Man.
You're in charge. Have you seen our project called? Yes, I use that. Okay.
Carrying two. My props. You're the only person who's excited for me to come up. Couldn't get a chance to walk out. So I say this to everybody that ends up looking at this. So our CTO at SupplyFrame, Alec Brodich, created this picture, and I fly a lot. So I decided at one point that if I put this as the backdrop on my screen on my laptop, that invariably anytime that you open up the screen on your laptop, the light's really bright on the plane, and the person sitting next to you kind of turns and looks at your laptop. And this is the easiest way to sort of diffuse that uncomfortable moment where they look at your screen and they know that you know that they're looking at your screen. So they look at this, and then for the rest of the flight, they leave you alone. So, hi, everybody. With that being said, so my presentation tonight, I'll kind of take you through a bunch of different stuff, was actually sort of imposed on me. It was encouraged on me. I was having a conversation with somebody about some stuff that I'm working on through a company that I'm a part of in China. For those people that don't know me, so I was one of the directors of product at Altium for the better part of about 15 years. I worked at Excel before that, which was a company that created a product called PCAD. So woohoo to the old guys in the room. PCAD was a schematic and PCB tool, which was very, very popular in the US back in the 80s and 90s, branded under a bunch of different things. Master Designer, Tango, which was actually Protel, rebranded in the US, variety of different stuff. So I've got a long background in the EDA space, okay? I spent a long time building schematic and PCB tools and driving different sort of product directions around schematic and PCB tools. So interestingly enough, I'm gonna take you on a bit of a history of, well, how we actually get to generative circuits and sort of the background. There's a big backstory to this. It kind of builds up to a moment at the end, which is hopefully the crescendo, which everybody applauds and cheers me off. No pressure. So concept of generative circuits, I'll get into in a minute, but the idea was started quite a while ago. So coming with a background in EDA, for those people that aren't really familiar with how schematic and PCB tools kind of came of age, I'm going to take you on a bit of a backstory that will actually build up to the concept of generative circuits and sort of what's actually happening with this company in China, and then some of the projects that I'm actually working on related to that. So for those people that don't know, a long time ago, schematic and PCB tools generally treated connectivity between multiple schematic sheets. The very sort of earliest systems only supported a single schematic sheet. When we introduced multiple schematic sheets, the original connectivity schema for multiple schematic sheets was that any off-sheet connection was made by a port, right? So in this context, the ports are represented by those little yellow boxes, and you can see the connections between those different things. There was no hierarchy in the original schematic tools. There was no concept of this sheet is a sub-sheet of this thing. So this is the power supply which belongs to this other thing. Hierarchy didn't really exist. Early versions of the Protel product, Protel used to be a product that eventually became Altium Designer. Early versions of the Protel product actually modeled schematic capture off of another very popular tool at that time, which was OrCAD. OrCAD later was acquired by Cadence and has been used now as a front end for schematic and PCB tools for a long time. OrCAD you might also be familiar with if you've used PSpice, because OrCAD is a great schematic front end to PSpice, certainly much better than the microsync front end that they were using. So in the early days, schematic capture sort of looked like this, okay? Over time, we introduced the concept of hierarchical or sort of multi-sheet schematics that actually had some sense of hierarchy and structure to them. And the way that the connections were actually made between the different elements here in this was that you would create very explicit top-level blocks, and those top-level blocks were representative of the sheet that was below it. So somewhere down there, I've got a block of circuitry. That block of circuitry is represented by one of those green boxes. Over there, I've got a block of circuitry, and those two things connect together. Now, this is a relatively new concept in the world of Eagle. Eagle just introduced hierarchy with like version 7, okay? But every sort of mature professional schematic and PCB tool, which sort of dominates the market space right now in professional companies, has this concept of hierarchy, okay? Over time, we introduced other concepts like multi-channel hierarchy. So the idea that I could take a schematic sheet and just by instantiating that same symbol multiple times, so stacking up those green boxes like they are here, I could actually create something which had multiple channels, okay? If I wanted something which had a 16-channel interface on the front end of it, I could represent that by a single block of circuitry, and then I could effectively step and repeat that block of circuitry. What the hell does any of this have to do with generative circuits? Just bear with me for a second. One of the things that we recognized over time was that there were all of these sort of standard forms. There were these things, these patterns that emerged in hardware. The way that you represent decoupling capacitors, the way that you handle pull-ups, the way that you connect individual signals into a bus. Well, you've got 8 signals going into a bus, or you've got 16 signals going into a bus. There are a few sort of complex buses, SPI, I2C, things like that, but they're pretty standard structures. So as we started to build out the Altium Designer software, one of the things that we added was this concept of snippets. And we really just borrowed this directly from the software world, because software development tools, good IDEs, have had the concept of snippets for a really long time. And we sort of borrowed this concept and said, what would that look like in the hardware space? Because there are all these standard forms that we're using as hardware engineers. How do we actually represent those as little blocks? So along the left-hand side, you can see, I mean, these are the snippets that are currently on my computer right now. Simple things like, hey, that's a 5-volt power port I have this habit of drawing things very dramatically. So I use red wires with a certain thickness which represent power. I have green wires which represent ground. When you read my schematics, if you can't read them, you're hopeless. It's not the Arduino schematic, certainly not the Arduino version 1 schematic, which was a complete train wreck as far as schematic capture is concerned. Yes, all of the components are there and all of the connections are there, but in terms of readability, it's just a disaster. So I have all of these things, these style things, and these kind of represent my standard form for things. How do I do pull-up resistors? How do I do decoupling? All of those other sorts of things. So we introduced this concept of snippets, and this was really sort of the beginning where we started to think about how could we actually make circuitry that was reusable, okay? So there are all of these things which we as hardware engineers, software engineers, whatever, do that every other company on the planet is doing. I feel, I charge into work just pumped up at the fact that I'm going to solve the USB problem for the first time, when every other company on the planet has solved the USB problem. Back in late 90s, early 2000s, it was, hey, I want to move from RS-232 to the USB port. So these companies emerged, FTDI was one of them, which gave us a really standard way to take all of this stuff which was on the serial port and move it to USB, because companies were demanding that, okay? Likewise, then it was, hey, I want to take whatever's on the serial port and I want to put it on Ethernet. Companies like Rabbit Semiconductor emerged. Rabbit Semiconductor, which is now part of Hddg, are the people that make those little XP modules. Those companies began to emerge as standard ways by which to take serial data and either put it on the Ethernet or put it on the Wi-Fi or put it over 802.15 or whatever, right? So these little modular elements started to kind of emerge as solutions to a problem. You had a choice. You could either solve it yourself, which most companies actually did, or you could go out and you could buy one of these modules, and those modules would sort of encapsulate that capability and then you would implement them. Later on, we introduced this concept in Altium Designer, and I'm not a sales guy for Altium. I don't work there anymore. I left there like 4 years ago, but I still use the software because I still believe in it. It's a great product. We introduced this concept of something called device sheets. And the idea with the device sheet is if I could take a block of circuitry, I could stick it onto a schematic sheet, and that encapsulated some function, something, that USB to serial conversion or something like that, which might have a couple of extra resistors or capacitors or whatever as a part of those things, that I could actually capture that into a block, and then I could place it like a component. So off to the right-hand side, just to explain what you're looking at, off to the right-hand side is a list of the device sheets that are currently on my computer. And that's a very short, kind of abbreviated list. If you look where the scroll bar is, I've got a shitload of circuitry that I've done as little modular blocks. Off to the left-hand side here, this green symbol in the center, which is very similar to those green blocks that you saw earlier, which has that little recycle symbol on there, is an indication of the fact that that's a device sheet. So it's a block of circuitry which we've done, we've encapsulated, we stuck in a box somewhere. Below that is actually what is behind that green symbol, okay? So that's the circuit which actually exists in here. Now, that one's somewhat simplified because there's only one component on it. So it's probably a kind of crappy example, but you could have any combination of circuits going on down there. So maybe it's an LDO, maybe it's a switcher, maybe it's your USB to serial converter, whatever it is, right? But you encapsulate that capability, you put it onto a sheet, and then you just place that block. We wanted to come up with a format that was a way of sort of treating those like components. So this concept of device sheets was the means to treat those things like components. And it didn't really take off. We introduced it into the software probably 8 years ago, 9 years ago, something like that, and the vast majority of customers weren't using it. And coming out of that, we formulated a team inside of Altium and said, well, maybe one of the problems is that people don't want to take these IP blocks and create them and then share them in the community. So we created simultaneously this community, and we asked people to come to it, and we were going to create this sort of sharing environment in which people were going to share these things. Now, mind you, this is 8 or 9 years ago, right? So this is a long time ago. We were pretty progressive in our thinking. There wasn't a lot of source code that was being shared. There weren't a lot of great open source projects that were out there. Arduino was in its infancy. You had PIC. PIC was kind of the leader in the entrance MCU, the sort of thing for the newcomer to embedded systems and that sort of thing. On the other side, you had a few other things that were kind of playing around in there. You had Propeller for Parallax, you had a few other processors. But for the most part, no well-meaning, well-organized organization was going to take their design IP, wrap it up, and then share it into a community. So we formulated a team inside of Altium at the request of the CEO, who was the guy that founded the company, Nick Martin, who was a good friend of mine. Going to see him a day or so. We formed a team inside of Altium called Design IP and Services, and I became the director of the Design IP and Services team. And the idea is that we would really look at what IP do people use in their designs. Library components is one example of that. So I spun up a team in Shanghai, 20 engineers, most of them new graduates, brought them in, and then we sat down and we started to look at the component problem. How do you create a schematic symbol, a PCB footprint, mechanical model for a part? Now, that sounds easier than it really is. Because if you just look at things like pin position on the side of a component, okay, we know that those oscillator pins should hopefully be, or those pins for the clock should hopefully be wide enough that I can fit an oscillator in between there, because when I draw a schematic, I want those pins to be separated so I can drop the oscillator in between there, have two capacitors hanging off of it, and that's kind of the standard schematic form for what that should look like. But what happens with multifunction pins? Oh, well, this could be I2C, or it could be SPI. How do I group those pins together? Do I group them in favor of SPI? Do I group them in favor of I2C? Do I group them according to the data sheet? Where do I put the power pins? What if I have an analog power pin and a digital power pin? What if I have an analog ground and a digital ground? Yeah, I know the ground should probably be towards the bottom of the component, but if those two things aren't supposed to be connected to one another, then where do I put them? Do I put one on one side and one on the other, all these other things? So just in the context of library components, this suddenly appeared to be a really, really difficult problem. We relented, and we ended up building roughly 300,000 library components, which is a lot. It's a shit ton of library components. 300,000 library components, which are pin accurate, have accurate PCB footprints, things that are built to the IPC specification, so you're following the 7351 standard. Before that, it was SM782, so now you're gonna take all your SM782 and test it against IPC 7351, and then there's 7351A, and there's 7351B. So you're building all of these things according to specifications. You've got this extraordinary amount of sort of external influence on just the quality of what the PCB footprint is gonna be. And we relented, we just continued to do it, right? The other aspect of that, which was kind of emerging in the software, was we added FPGA capability to the software. And this was very much driven by the CEO of the company. The CEO of the company said, look, FPGAs is sort of the ultimate reconfigurable hardware platform. So if I can take a block of something and just deposit it into an FPGA and add SPI, or add I2C, or add, I don't know, a video controller, or add an Ethernet MAC, or these things. I have sort of the ultimate in extensibility. So we made a full head-on run at the FPGA space. We acquired a couple of synthesis tools, we integrated them, we built a better synthesizer, we created FPGA or VHDL and Verilog compilers, we had all of the parsers working, we have all of this capability inside of the software. All of that design IP was stuff that we authored. So then we started building 32-bit processor cores. We started looking at core compatibility. So we looked at Wishbone as a standard for the buses. So different IP cores could connect together with one another. Wishbone, if you don't know, is just a very simple bus interface that allows you to connect IP cores together and resolves the interface between those two different IP cores. Okay. Wishbone also has standards for things like an interconnect, which is particularly useful when you're doing something like a processor core. The interconnect allows you to memory map the peripherals in the FPGA to an address range in the peripheral memory space of the processor core, because you have to remember in the FPGA space, the processor is just the core. The peripherals that you pack around it, you have to tell it where those peripherals exist, what's the base address, what's the address bus width, all of those other sorts of things. In the case of direct memory access, you need arbitration. You need all these other sorts of things to start to kind of play into that. But it gave us this incredible sort of insight into what could probably scale all the way through to the hardware space. So we started in a design IP and services team to start building a lot of little modules. We started to play around with circuits, and we said, okay, let's see if we can just build a bunch of circuits, things that sort of handle different capabilities and encapsulate those things. And let's solve hard problems. Let's solve wireless. Let's solve the analog front-end problems. Let's solve high power, those sorts of things. Let's encapsulate those capabilities, and then people can just grab it and they can place it, right? So along the right-hand side, what you're seeing there, there's a SIM900 module, that's the 3G module. There in the middle there is a roaming networks module. Off to the left-hand side is a homegrown 802.15 module. Eventually, I resolved the whole the 802.15 module to this little guy down here, which is based on the AT86RF, which is roughly the size of a paperclip, but encapsulates 6-LoWPAN Zigbee 802.15 into a board. And you'll notice that the castellated edges of the board was our first attempt at this. We wanted to build little modular circuit elements that people could just grab and they could place into a board. We thought, hey, at this time, the sort of trend is castellated edges. There's a huge limitation with castellated edges. The smallest that you can probably go with castellated edges and do anything respectable is 50 mil pin spacing. Now, 50 mil pin spacing doesn't translate then to the breadboard environment. But at 50 mil pin spacing, anything that's got a large number of I/O, by definition, is going to take up a huge amount of board area. So we started to wrestle with this, and we built a lot of modules and a lot of stuff following castellated edges. So down here, there's a camera, you've got an IR interface, you've got a CPU and programmer, you've got some other stuff going on. Over there, there are a couple of H bridges. You've got some high-side drivers, low-side drivers, a whole variety of different stuff. I tried to put the ruler in there so you would get a sense of what the size of those things were. So I'll pass this around. This was a combination of some of the castellated boards and then some of the CPU boards. You'll see antennas and a whole bunch of other stuff on there. Most of my background is in radio or kind of the FPGA space, sort of two diametrically opposed sides of the spectrum. But here's a couple of examples of some of the boards that we were actually doing, and you can just kind of float them around and take a look at it. So we started to build all of this IP. Now, interestingly enough, prior to this, Altium had built really 3 FPGA development boards, Nanoboard 1, Nanoboard 2, and then the Nanoboard 3000. We also built this thing called the Live Design eval board. But the sum total of 5 years of hardware development at Altium before I took over the hardware team was roughly 4 circuit boards. Now, they were elaborate, mind you. These were FPGA boards. They had hot swappable FPGAs, so you could say, hey, today I'm working on Altera, I'm gonna pull that off, I'm gonna drop in a Xilinx chip. And all of the IP was designed to be vendor independent. So it has this tremendous capability of allowing you to actually test what the FPGA system performance would be by just hot swapping different FPGA boards in there. Reality is we built it, but we built it probably 7 years too early. Nobody cared. The people who were doing FPGA development were stuffy guys in lab coats sitting in the corner that didn't want anything to do with anybody coming into their wheelhouse and saying, hey, we just made FPGAs easy. It just wasn't well received. So here's some more examples of some of the module boards that I built over the time that I was there. And this is an particularly interesting one. We were playing with a lot of different concepts. So this one, on the edges of the board, it's very difficult to kind of see from where you are actually puzzle piece edges. And inside each one of the puzzle piece cutouts are 3 pads. When you put the 2 pieces together, if you run a bead of solder across them, it makes a connection, and they're almost impossible to crack apart. They're almost as durable as a regular board. The idea with the puzzle piece edges, and it was really hard to find somebody who could manufacture it well. But the idea with the puzzle piece edges was that I could separate different sections of the system. And you could say, hey, this is the intelligence of the system. And this is the front end. And this front end might have some sensors, it might have some controllers, some motor drivers, whatever it is. On the back end of the system, it's just this intelligent module, that sort of thing. So this is actually an example of that. You can see along the center here, that solder line there is actually a bead of solder that ties those puzzle pieces together. okay? You slide the two pieces into place, they snap and fit, you run a bead of solder across it, bang, Bob's your uncle, everything's great. Here's an example of some of the front ends, and those front ends are really that top section here of that same board. So this bit up here. It allowed us to create all of these sort of interchangeable type things. Now, all of this stuff is happening in R&D. We're playing around with a lot of these ideas. Reality was is very few of them ever saw the light of day. So there's more of the puzzle pieces board. This one over here was actually particularly interesting. With the castellated boards, we started to build these standard land patterns for the castellated board to land on. And then we built breakouts for them. In this case, that breakout is actually two sections that are V-scored. And the idea is that you might have 3 boards that you put on there, you might have 6 boards that you put on there. Depending on the board configuration that you wanted, you might want to crack those two pieces apart and just have a connector on one end of it and plug it into a scope and test it out. So as I said, simultaneously we were working on all of this FPGA stuff. Because we were doing processor-based FPGA design, we acquired a company out of the Netherlands called Tasking. Tasking is very much known for compiler support for the DSP, the 56K, compiler support for all of the Infineon chips. So we became the sort of go-to compiler developers for the Infineon chips. Our Drystone, Whetstone results blew Altera's Neos compiler out of the water, okay? I mean, huge orders of magnitude performance improvements over what Altera was capable of achieving with the Neos, okay? We put in an extraordinary amount of effort into developing not just the FPGA system, but also the embedded software system. So let me explain what you're looking at. On the left-hand side is the top-level schematic for an FPGA system. The components like this touch screen over here and what looks like memory over there are actually representative of components that are on the board. Everything that's going on behind that green block right there is what's happening inside of the FPGA. Now, one of the guys that works for SupplyFrame was actually instrumental in the development of this system down here at the very bottom right, which we called OpenBus. One of the things that we realized really quickly is that if you had standard bus interfaces between all of the IP, then what was the point of drawing all of the signals? There was actually no value in that. So schematic capture by itself was somewhat under threat. If I had to draw all of the signals in there, it was purely a busy work exercise. There was no value in that. If these things had a standard wishbone interface that allowed me to connect block A to block B, then why don't I just draw a line between the two? So we created this concept called OpenBus, and let me just explain kind of what's going on over here. Pull this out for a second. So at the center of this is the TSK 3000. This is a MIPS 3000 derivative core, okay? Off to the left-hand side is what's called a wishbone interconnect. And the wishbone interconnect is a standard wishbone component. It's not something that Altium created. It happens to be a component that's part of the wishbone standard. The wishbone interconnect allows you to memory map the peripherals into the processor's peripheral memory space. That allows you to say, hey, this peripheral lives at base address XYZ, and its address bus width is this, and its data bus width is this, okay? So this is a processor core here connected into the wishbone interconnect, and then hanging off of there are a series of different cores. This happens to be an LED driver. This happens to be a touch sensor core, which represents this touch screen, which is over here. That's actually the touchscreen controller core. Down here is an SPI core. By connecting those into here, you would double click on that and say, the base address of this is this, and then you just start addressing it. And it doesn't matter. You can say wherever it exists because it kind of doesn't matter at that point. It just needs to resolve the instructions that you're writing at the software level to some location in the processor's peripheral memory space. Off here, there's a multi-master which happens to handle the interface both between the touchscreen and this external memory over here and the processor in the external memory, because the processor required external memory for this application, okay? So that's basically your arbiter. And it's saying, hey, I've got a touchscreen which needs access to this memory over here, and I've got a CPU. Those two things, I have to do some arbitration. Who gets this? Is it round robin? All of that sort of thing. What's interesting is off to the right-hand side here, after we acquired Tasking, we started to develop then all the software drivers and services for all of these different cores. And what you see over here is a stack of software drivers and services. And one of the things that we got somewhat frustrated by was the fact that you would spend a lot of time in init functions setting up all of these different peripherals. when really that was just largely a waste of time. You could almost do this better if you just gave somebody a table with all of the different peripheral settings, and then you said select between these things, and we'll go ahead and automatically generate the source file. So we'll generate all of the init routines for you based on the parameters that you tell us. So we built this thing called the software platform. And the idea with the software platform is that you would come in here and start selecting, hey, I've got a VGA interface. Then when you selected that off here, we would give you a list of all the parameters for the VGA interface. What are the screen dimensions? What's the refresh rate? All of the other things. What's the source clock? All of those things. And you would just come in there and kind of plug it in. Made it super, super simple. Mind you, all that capability still exists in the software. But again, we were probably 7 years too early. The vast majority of Altium users who are paid license users never used it. And it was tragic. At this point, it's genius. But unfortunately, the concept somewhat diverged away from where they wanted to be. They really wanted to move back into schematic and PCB and double down on schematic and PCB. So as a result of that, myself and down below, that's Nick Martin. He's the guy that actually founded Altium. We both left. Nick left first, and then he and I took all of the stuff that we were doing in the Altium context and said, how could we actually do that better? How could we do this and do this right? How could we build a company based off of that? So he and I started a company in Shanghai. It's actually a Hong Kong-based company, but it exists in Shanghai. And with all of that modular circuit stuff, we had the other coincident event of this large push into IoT. And with IoT, that suddenly brought this whole web world now into this space, because hardware developers know jack shit about writing JavaScript. I'm sorry, I'm the first one to admit that I know nothing, okay? When I get into that space, I'm like, wow, this is, you mean oh, that's an object. Oh, shit. Oh, okay. So we struggle with it, okay? And candidly, the ratio of software developers to hardware engineers is about 30 to 1. So there's this massive blue ocean that exists out there. Inside of Altium, what we were hoping to do with some of the modular electronics was to be able to introduce that to software developers in a way in which you didn't have to think about the hardware that was behind those things. When we left Altium, then that became kind of the mission. And we said, all right, cool, let's just see, let's double down, we'll put a few $1 million into this and let's see what it takes to actually do this right. And interestingly enough, the first thing that emerged was that electronics is not infinitely subdividable. It's just not. Even if you take some complex area like sensing, how many sensors do you really use? Right? You've got temperature, barometric pressure, altitude, which is a function of barometric pressure. You've got what? Linear motion, you've got rotational motion. You've got a variety of different things, but there's just not that much. So we just said, okay, well, what does that problem set actually look like? We began to kind of enumerate everything behind each one of these different categories. When you look at communications, how many communication standards do we use? We use Wi-Fi, we use 802.15, which, it's a bunch of shit in there, 6LoWPAN, you've got Zigbee and a bunch of other stuff that's kind of wrapped up into there. But the reality is there's just not that much. What else is there? Ethernet, serial, there's just not a lot, at least not as far as device-to-device communications is concerned. And certainly in the context of IoT, that actually narrows the funnel even more, so you're more focused on just a really limited subset of things. You've got Bluetooth, Wi-Fi. I don't know of a lot of IoT devices that are looking to build Ethernet into it, right? I mean, there are some which have sort of doubled down on the Zigbee side of things, but I don't know where that goes. I know it's an interesting concept, but I don't know that that's actually going to emerge as the standard. Because there's then no interface to the mobile phone, it's not an easy interface to the web browser. At some point, you're going to have to broker every transaction. It's kind of a shit thing to bet on. If you look at power, you've kind of got linear switch mode, right? And most of the stuff that we're talking about, certainly in the IoT space, which is kind of the largest emerging market that we have right now, kind of isn't that complicated. The voltages are relatively low. There's a few things that you're going to want to switch, like lights. Okay, great. So you need some SSRs and you need some SSR controllers and things like that for those sorts of things. If you want to do dimming, then you're going to do some zero crossing detection and some other stuff. But it's just not that much to think about. Okay? So we decided to double down and see what we could do. And so we enumerated what we thought was the list. And then we went to town. and we built a shitload of modules. All told, we've got about 600 of them that cover every aspect of everything that you could ever want to create. So I'm going to pass around, first of all, here are a couple of the panels from some of the modules. And the first thing that you're going to notice about the modules, which you can see reflected up there, is that we got rid of the castellated boards. Castellated boards were just a shit approach to it because it was just way too big. My wife's mobile phone would be 6 times as big if we did everything with castellated boards. So that wasn't going to scale. That wasn't going to be a way to go forward. And the only way to really move forward was to try to get a lot of pins in a small area. The only way to do that was to actually build boards with BGA pads on the bottom side. Now, this last weekend, hand-waving moment, I ran a workshop, and I'm running it again on November something, 1st, showing people actually how to reball BGAs. We're actually doing it with a PCB which has BGA pads on the bottom side. And then I will actually take you through the process of stenciling the board, getting the BGA down, we'll throw it into a reflow oven, and we'll make it work. Alvaro, who's standing in the back of the room, was one of the people who got all the way through that process and was successful the first time. In fact, every person who went through that process was successful. So the fear of BGAs is totally unfounded. The most difficult thing to do with BGAs is test them. But the process of soldering BGAs, as long as you temp the vias, is actually really, really easy. As long as you've got a stencil, you've got paste, and you've got a little bit of patience, you'll get it right. And chances are you'll get it right the first time. Because underneath that, you've got incredible surface tension. It's going to pull the BGA into place. As long as you're not shit with the tweezers, you'll make it happen, okay? So you can see that now we ran into some problems. When we wanted to do high side drivers and low side drivers and some power FETs and things like that, we needed to actually build things which could handle the heat. So we started to build basically what were the same sort of thermal pads that existed on QFNs. We started to, excuse me, build these sort of larger rails here as well when we needed to be able to carry more current. So those things like the SSRs and stuff like that, where I was going to have a lot of current going through it. I've got 10 amps, 240 volt. Holy shit, how do I power that off of this little crap module? All of that isolation and things like that we had to work through, so we built all of the isolation. Now, again, just reiterating the point. So none of this is infinitely subdividable. And in fact, every one of us solves the exact same problem as everybody else as hardware engineers. We go to work and we think like, hey, you know, great, I'm gonna go ahead and I'm gonna build this, I don't know, FET driver or something like that. And that's not the first time that that problem's been solved. It's not the last time it's been solved. In fact, you're probably duplicating the same schematic that's in the datasheet that was duplicated by 65,000 other people before you. So we started to explore then kind of other concepts in the IoT space. And IoT is itself a much larger problem than generative circuits. But just to give you a sense of what we were building, we said, okay, at a bare minimum, we need the hardware. But then we need the embedded software drivers and services and things like that. We need some JavaScript on top of that. We need a cloud. We need a place to store the data. Then we need a security model. Pretty soon, this thing started to just grow and grow and grow and grow and grow. But focusing explicitly on the hardware, initially when we started to do those little modules, and I'll pass around, this is the real money shot right here. So I'll pass around some of those modules so you know that I'm not full of crap and that's not just a really good render. So I'll pass around some of the modules. All of them work. Have a look at kind of how the different things are stacked up and the way that they actually kind of appear. Originally, we started where you could put multiple BGA modules on the same breakout board. And the idea is that we would sort of follow the Spark model or some other model, I don't know, and say that we're going to consolidate a bunch of capability onto a circuit board, and that was going to be your development board, and you would develop your system on that. And we reached a point where it actually proved not to be a great idea. Instead, we reached a point where we said, if we really just focused on a single module per board, and every pin on that board was broken out to the breakout pins on the DIP package, then what you could construct on a breadboard was in fact an exact one-to-one copy of what you would create on PCB. You would put this board stacked with this board stacked with this board stacked with this board next to each other along the length of the breadboard, and you would have one-to-one exactly what appeared on the PCB. So now you had a prototyping platform which was a true reflection of exactly what the PCB would be like. The only thing that was missing were the connections in between the individual boards. And whether that was done using the BGA module or it was done using the DIP package that we broke it out to, it didn't matter. It was just a series of connections. So this sort of brings us to the concept of generative circuits, but not yet. So for all of those different modules that we created, we then went through the process of actually developing a whole embedded software stack for every module. And we said, okay, it's got to have drivers, it's got to have services, it's got to have examples, it's got to have all of those capabilities. So we wrote a shit ton of code for every one of those different pieces. Then we encapsulated it up in the same way that we sort of did with the software platform, which I showed earlier. We said, okay, this is all of the drivers and services. It's really just a series of parameters which define this implementation versus that implementation. Let's separate those things out in a hard way so we can isolate the different elements and we can start to build an embedded software system which is really scalable. So that kind of brought us to this notion of what is the thing that you're actually trying to implement. At the end of the day, my wife doesn't care whether her mobile phone has chip A or chip B. She cares whether or not it has a certain capability. She's looking for an experience. And what defines a capability in the IoT space? Well, capability in the IoT space is defined by a whole bunch of different things. There's a hardware component, there's an embedded software component that goes along with that, there's a security stack, there's communications back with the database. That database is fundamentally going to interface to JavaScript, probably through JSON or something like that. On the front end of the database, who knows? However you want that to talk to the hardware, there's got to be some standard stack there. There's got to be a security stack in there, so there's got to be certificate exchanges, probably pre-shared keys, a bunch of other stuff, unique identifiers for all of the different boards and all of those things, so the system can be truly hardened and protected against outside intrusion, and then also make it possible so you can open it up for other people to participate in that space as well. So we said, let's just focus on capabilities. So with that huge pile of modules, then we said, okay, now the charter is we need embedded software drivers and services for every one of them. We need a driver in JavaScript for every one of those things. We need some standard form to talk to those things. And this is actually when it started to get interesting, because here are two old school schematic and PCB guys, Nick Martin and myself, who have been doing schematic and PCB shit for almost 20 years, who looked at this and said, okay, our original model, if you replace that with FPGA, was that from the FPGA, we could infer what embedded software you needed. Okay, so what IP cores you selected from that, we could infer what embedded software you needed. From that, if we knew what the hardware platform was, then we kind of could almost infer, just from this level, what that full stack there, those first three kind of layers looked like. At this point, we sort of looked at the top end of this and we said, okay, in the cloud context, you know, you've got all of this other shit up here, somewhere up there is JavaScript. If I say in JavaScript that I want to sense temperature, maybe we had this all wrong. Maybe it's totally flipped on its head. Maybe it's not working from the hardware up, but maybe it's working from the software down. Maybe instead of starting at the hardware and building the hardware platform, if you could just start in JavaScript and say, hey, I want to sense temperature, so I include the temperature library. And at the moment in which I include the temperature API, the software can say, oh, that resolves to one of these 6 modules. What precision are you looking for? What's the high temperature? What's the low temperature that you're looking for? What kind of temperature are you trying to sense? From there, we could almost tell you exactly what hardware you needed. In fact, we could tell you. So that began this process of generative circuits. And we started to play around with this concept, and we're still very timid about just opening it up to the real world. 100% yet. But here are two guys who are veterans in the schematic and PCB space. I mean, we know how to build a CAD tool. And here we've built this system now, which from what you're seeing on the right-hand side over here is actually just simple JSON. And in there is actually a list of what components you included. And that's all done by background compilation of the embedded software code that you're using or the JavaScript that you're writing. So by looking at that, we can actually extract what components you need, and we can tell you exactly what the connections need to be. Now this raises something which is kind of interesting. The net that comes out of that is that, first of all, if we can identify what the capabilities are, what you're defining, it doesn't matter where you start. You can start in hardware, you can start in embedded software, you can start in JavaScript, it doesn't matter. But if I could identify what capabilities you were trying to implement, just simple background compiling, I can do that. Then I could actually define what hardware you needed from that. I could go one step further and say, hey, you need these embedded software drivers and services that actually go along with that. And I could actually tell you what the connections were. Now, this is not about running JavaScript on an MCU. That's not interesting to me, because that will never meet the kinds of requirements that I need in a production product. Never. 0 times. Absolutely 0 times. Big fat goose egg in my work. Okay? I'm sure it's interesting to somebody, but it's not interesting to me. I've got real-time requirements. I'm trying to build industrial control systems. I'm trying to build commercial real estate. I'm trying to do things that are truly the essence of IoT, where the aggregate of information is really the basis of everything that I'm doing, and I've got to aggregate that across a bunch of devices. It's not about running JavaScript in an MCU. If I'm standing in front of my toaster and my phone pops up and tells me that the toast is done, that's a shit example of a problem. I'm sorry, I'm going to go on record and say it. Interestingly enough, if you've been around the CAD world for a long time, are there any other files in the CAD world which represent things in terms of components, their various pins, and then their connections? It's a netlist. So from this, we were actually able then to extract a netlist, which we could bring back into a design tool. And sans any kind of schematic, starting at JavaScript, I can actually generate a netlist which tells me exactly what I need at the PCB level. So I don't have to draw a schematic, I don't need to create any connections. The beauty of those modules is I can go with as many layers as I want. That doesn't matter to you. So yes, they have BGA pads. Yes, they're complex. Yes, I'm using 4 mil tracks and 4 mil spacing. Yes, I'm doing all sorts of crazy shit that's really hard in PCB, but that's not your problem. As a JavaScript developer, that's not your problem. That's my problem. And if you open it up, then it becomes the problem of every hardware engineer who wants to participate in that space. Now you've created something which has truly the potential to catalyze then this whole software developer community to be able to participate in the hardware world. Because fundamentally, the hardware is just the last mile. As a software developer, somebody wants to reach out and touch the real world. That's it. So they build all manner of kludge systems to try to get out there and reach out and touch the real world. The real world is fundamentally hardware, it's fundamentally analog, it's complex, there's a lot of physics, there's a lot of math, there's a lot of those things, but if we can encapsulate those things and actually make them available, and then build a platform that allows people to contribute into that space, then you have the potential to really create this sort of massive change and open it up to 30-to-1 software developers to hardware engineers. So we're right at that stage where we're teetering on opening it up. There are a few little fine-tuning details on it. This is an example of an old school PCB netlist, which happens to still be the same Protel netlist format that was used in Tango DOS. We never had any need to change it, because fundamentally on PCB, what is it? It's a list of components, a list of their pins, and what do they connect to? That's it. There's nothing else that I need to embed in the netlist. And if I can tell you already that from JavaScript, I can tell you this is a component, this is its connections, these are the other components that it connects to, then I can actually generate a PCB from something that you're writing in software. And again, it's not about writing JavaScript for a processor. It's about leveraging the capability that people have in the JavaScript world and allowing them to then reach out and actually touch real hardware. So off to the right-hand side, for those people that are kind of uninitiated, this is the netlist. These connection lines that are over here just represent those physical connections. And this is a board, which is floating around the room, which was derived directly from the system that I showed you earlier. So I'm able then to produce a PCB from source code. So the concept of generative circuits is actually this concept of, hey, can I actually open this up to allow a whole new world of kind of people to participate in this space? And then how does that change the form in which hardware engineers participate? It's not to eliminate the hardware engineer. Because those boards, most of them that are floating around the room are 6 layers, 8 layers. There's a lot of blinding Berry vias in a lot of those things. It's hard to get stuff into a BGA package like that. But the manufacturing costs on those are incredibly low. The operation is all handled out of Shanghai. We went off to move to Shanghai. We stayed around. So that said, that's kind of all out of me. That's the stuff that I'm working on when I'm ready to open it up for everybody to charge at it, and I'll let everybody else participate. Any questions?
Okay, 2 if I remember them. The first one is, so from the user interface layer, you can say, hey, I want to be able to sample a temperature sensor within this range of this temperature, this frequency, and then I want to be able to publish that information to a web page. You can take all that desire, that's a script basically,
Exactly.
turn that into, okay, you're going to use these modules. Does that also include the software that would actually interact with them?
Yeah, so the embedded software drivers and services and everything are actually already done. So that would implement all of that capability. And that would then be enumerated in the embedded software side of things. Now, right now, the piece that we're tooling on is how do you actually get the embedded software code to do those things at that level. So there's a bit of work to do in that space, but I can tell you that it's actually a knowable problem. Like at this point, it's a knowable problem. It's a hard problem, right? But like when Altium Designer moved from a PCB editor that was based on OpenGL to a PCB editor that was based on DirectX, so we could do all this 3D PCB and shit like that, that was a hard problem. But we ran at the hard problem and we solved the hard problem, and we had this incredible PCB editor that could do real-time 3D and PCB editor and all these other things. So yes, it's a hard problem, but hopefully we have a history of solving hard problems, and this is just another one of those. So,
I guess the second one is, does the parametric instantiation of hardware, of FPGA hardware, FPGA logic, still exist in Altium?
it does. It does, but it's really, but I won't go on record as weighing in good or bad on that. I don't know who's supporting it. Let me put it that way. It was sort of deprioritized, and that much is public knowledge. It was deprioritized at one point when the company went public and said, went public a long time ago, but when the company went out and said, listen, we're really going to double down on schematic and PCB. So those were things that Nick was dreaming about, and Nick is very much a forward-thinking guy. The first paper that I got from Nick on connected devices was 12 years ago. And he said, we need to build a bunch of hardware IP so people can build connected devices. And we need embedded software IP and FPGA IP to support that. And that was 12 years ago. There was no IoT, nobody was thinking about any of that stuff. I mean, hell, I've been putting stuff on IP networks since the 90s. But there was nobody had really thought about it in that way. So it was just pretty forward-thinking dude. And I think basically what we did is sort of run out of runway with some of that capability, at least as far as how do you continue to sell that to a board who is looking to maximize shareholder value.
Yeah, it's super cool because there is a whole level of design that does not necessarily need to be done anymore because it's been abstracted away.
Yeah.
But yeah, this is super awesome.
Yeah, it's fun. It's a fun, it's a fun project. It's been a fun project, and there's a shit ton of source code and a lot of design files. So as soon as we go public with all of it and release everything, there'll be more hardware than anybody could probably shake a stick at. I mean, there's a lot of stuff in there. Like, we've tried to think of everything. Yeah.
What do you think this disrupts? Does it fix common sense? You can see semiconductor or component suppliers getting roasted up because nobody fixing it.
Well, so I think actually what it does, so I don't know that there's a history of that being sustainable over the long term though. I think modules are never a sustainable position. Modules are a sustainable position until the market opportunity is created for the semiconductor manufacturer who says, let me consolidate all of that into a chip. So if anything, what it does is it lights a fire on them to set underneath them to say, okay, what capabilities do we really need to include in devices going forward? If they see that there's a huge amount of money being made on module A or module B or module C, they'll consolidate it into a chip. But I don't know that that's a direct threat because there are some things which don't kind of make sense to do that, right? There's just not enough of a market for that. And those requirements are going to constantly change. They're going to constantly evolve faster than the semiconductor manufacturers can keep up and consolidate things such as. We just know that that's going to be the case. I mean, we've separated out whole communication stacks previously in hardware that now are a single chip, and you talk to it through a UART. So that model will continue to exist because they'll never move as fast as where the market wants to go with things. The technology that consumers demand moves faster than the demand from the design engineer back to the semiconductor manufacturer. But I think in terms of who it actually disrupts, I think if anything, it disrupts the software world, but in a positive way. Because fundamentally what you're talking about is, how do I make it possible for somebody to reach out and touch the real world? Because that's really what the IoT game is all about. How do I reach out and touch the real world with a software application? So the real world is just an extension of my software application. And once I can get that data and I can aggregate that data across multiple sources, then I can do things with it, data analytics on top of that, I can do some averaging, I can do all sorts of different crazy shit with it. But most software engineers can't participate in that space without having these other people brought on board to be able to solve those problems. And then, the career opportunity for that other group of people depends on them solving each one of those problems. So I guess there's some disruption for the hardware engineer, but I think it's more a retooling. It's about, okay, well, how do I change my value? So my value is about how do I create these things which are unique to our products. And then at some point, when we start to share those things out there, then maybe there's more opportunity for them. I'm not totally sure. But in terms of the proportion, the reason why it's not scalable right now, it's not sustainable right now, is just because there's not enough hardware engineers to meet the demand that the software world is going to create. And so now software engineers are trying to play in the hardware space because that's the only direction that they have to go. Is if I want to get shit done, I've actually got to build the hardware myself. Or I've got to hire a hardware engineer, I've got to pay them $160,000 a year to come on board and actually build shit. And either one of those two things is probably unnecessary, right? Or just uncomfortable. Anybody else? Yeah.
So let's say I pick a bunch of modules, or I want some capability and suggest a bunch of different modules and create a netlist. Who actually lays it out on the board? So I'm combining these modules. You can do an auto router with constraints.
Well, it's interesting because once you simplify it, then the concept of auto routing actually sort of reemerges as potentially, mind you, Chris is shaking his head, but he's shaking his head because he's always used shit auto routers. I mean, the concept of auto routing looks like it could make a little bit more sense. You might need to go into a PCB tool, but if you are a person that's entering into PCB for the first time, things could be infinitely simpler. One of the things that's interesting about the VGA packages is that if you stack them on opposite sides of the board, first of all, not only with the VGA pads to the board do you get a super low impedance, super short path to the PCB, to the carrier PCB, much better than the connector that you're going to plug it into. But then you also have the ability to stack another adjacent thing on the bottom side of it. Or you could even conceivably build them in a way which you can stack them on top of one another too. So routing is an interesting question. I don't know that there's a simple answer to that, but there are a lot of sort of assisted routing. Like, I don't know if anybody's seen the video from Mentor for their, what is that, sketch routing? If you haven't seen Mentor Graphics sketch routing video, I want you to watch it. It is absolutely amazing. So Mentor, I worked at Altium for a bunch of years, but Mentor has hands down the best routing in the industry. And if you look at their sketch router video, it will blow you away. It's amazing. The guy routes DDR tracks in under 3 minutes. I mean, it's insane. Like all of the DDR bus, like just, oh yeah, that's done. Shit. So I'm not sure. I'm not sure. It could be that somebody still has to go into something other than Eagle, which doesn't have collision detection for routing and route a PCB. But I don't know that that's the end of the word. Yeah.
So I really like netlists, and I like the netlist focus of it. I've debugged a lot of netlists, and I've debugged a lot of schematics. And the netlists are harder to debug. So I wonder, how do you work in debug and test and those things when you don't have a schematic?
So it's interesting. I mean, mind you, I'm not opposed to saying, hey, I need to create a schematic from these things, because the blocks themselves are actually simplified. So just to give you an example, me try to move my mouse here in a way where I can actually move it. So, oh, lo and behold, Altium Design. He had it open on his computer all this time. Just keep losing my mouse. There we go. So I'm going to open up a project, and I apologize that it's going to take me just a quick second to do it because it's up here in my GitHub. So this is a project that we used for the workshop this weekend, and afterwards I'll show anybody who's interested the design, the actual files themselves for this. But let me give you a sense of kind of how this looks. So over here on the right-hand side, so this was a board that was supposed to be V-scored. Notice the notes, it said, hey, V-score on these lines, and the README that went along with it, and the email that went along with it, and they came back and they weren't V-scored. So this is a carrier board which breaks out the breadboard, or sorry, breaks out the BGAs to a DIP package. So this is actually what's actually in that workshop. So I take people through this in the workshop, and we actually go through this process of building all these things. These are 3 of those little BGA modules which are floating around the room. In this case, I simplified it. I just put some LEDs on one side of this, and then the BGA pads on the bottom side. And the reason I did that is because in the workshop context, somebody could solder this on here, drive those pins, see the LEDs light up, and say, oh, good, I have a good connection on my BGA. Great. And that sort of dispels the fear and anxiety around BGAs. Anyway, so with these, as far as the schematic representation of that is concerned, I actually built a schematic for all of those. And so this is that circuit which sits on top of that BGA module. That circuit is just broken out. And these are just components. All I did with the components is I just turned the pins facing inward, and then I put the schematic sheet on the inside of it. So instead of the pins facing outward and then me making all the connections from the outside, I just said, okay, well here's one set, one set, one set, one set for the 4 sides of the BGA. And then I just ran the connections between the pins over there. So this is actually the BGA module, and then this is the circuitry which is sitting on top of the BGA module. So I could actually extract all of that. It wouldn't be that difficult to say, yeah, actually create me a schematic which shows me what the block diagram for some of these things are. And it may be at the level of the carrier board. So if we look at the carrier board level of that schematic, that's got basically those 2 BGA modules on the carrier board, which if we sort of reflect back on the PCB, are these over here, right? So this is a carrier for this, it just breaks them out onto a DIP package, right? And those are just a series of connections that are made then into the pins on the outside of that. So I could actually generate a schematic from that. It wouldn't be that difficult. It's actually not that hard. It's a time-consuming problem, but it's not a complexity problem. It's not a sophistication problem. Anybody else?
So even if you generate a schematic, it's kind of like going the other way around, because I think the idea is that between your interconnections, you have agreements that will always be held, which makes the whole system digital, so you're designing on a higher level. I think you might understand.
Yeah, and I think, so yes, but I think to the seasoned hardware engineer, there is the risk that somebody is going to want to be able to debug it at some point. They're going to want to get their eyes in there. And I think the one thing that Nick and I have learned over the years is that you can't hide things. You can't obfuscate things to the extent that people can't actually see how these things go together, which means that you have to create a form in which you represent that is, that can be understood, right? That can be read very easily. I agree, a netlist isn't a great thing to read. It's a shit thing to read. And to try to debug things on a netlist isn't great, but to go from a netlist to something which is graphical is actually super easy. And in fact, to generate a netlist, we would be going to JSON first. So we would have the JSON data, and from that, we could actually build a schematic relatively easily by saying, place this module and draw a line from here to here, right? And you've got some drawing problems and things like that. But again, Nick founded Altium, like he knows how to draw stuff. So I don't know that any of those things are things that we can't overcome. All right, so I'm getting a wrap it up signal at the from the back of the room. If anybody's interested in the workshop, to actually go ahead and build these things. So I'm running the workshop again on November 1st. I also do another couple of workshops on like, just learning how to use schematic, generate, manufacture, production circuit boards, things like that. The workshops are generally free, and they run the whole day on one weekend day, usually from like 10 a.m. to like 7 p.m. They always run over, but it's okay. If you go to Meetup and just find me on Meetup. My name is up on posters up there too, so yeah, find me on Meetup. One other thing that I want to mention before we take off. So Hackaday is actually hosting a super conference, and I just want to mention it again. So the 14th and the 15th of November, Hackaday is running a super conference. It's actually going to be held at Dogpatch Studios, so it's relatively close, easy to get transport there. There's like 2 trains within 5 minutes walking distance from there. Buses go there, amenities there, all that stuff. It's going to be amazing. We have some amazing people coming to give talks, and a lot of workshops, very hands-on oriented type stuff, like actually physically doing stuff. And then also, of course, we'll be announcing the winner of this year's Hackaday Prize, which happens to be like $250,000, which is a big deal. And there's a $100,000 best product prize, which will also be announced at the event. So, or a trip to space. So it's up to the winner. Last year, the winners didn't take the trip to space.
196,000.
196,000. Oh yeah, it's a monster number, right? Yeah. Okay. So yeah, it's the monster. Okay. Anyway, so that being said, Chris Gamble. He's got nothing else. All right. Thank you. That's it. That's it. Yeah, feel free to stick around, you guys, if you want. If you want to have another beer, if you want to go to get a shot of the Empire.
All right, thanks.
Hey, so how do we follow lines?
So I've got a bunch of stuff which I'm pretty legit with announcing stuff. So probably and we'll run a so, like, just sort of